What if the second largest object in the inner solar system wasn't a planet at all, but a moon? Think about that for a second. You probably grew up learning that the biggest things out there, besides the Sun, are the planets. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. That's the list, that's the hierarchy. But somewhere in that lineup, hiding in plain sight, there's a cheat code. Because right there, orbiting Jupiter instead of the Sun, is a world bigger than Mercury. And it's not a planet. It never was. It's a moon. A moon that broke the rules from the moment it was first spotted through a telescope in 1610 by Galileo Galilei. Let that sink in. Mercury, the smallest planet closest to the Sun, roasted to over 800 degrees Fahrenheit during the day and frozen to minus 290 at night. That entire world is smaller than this moon. Ganymede has a diameter of about 3,270 miles. Mercury? About 3,032 miles. That's nearly 240 miles of difference. So if you could rip Ganymede out of Jupiter's orbit and toss it into the inner solar system, it would be a planet. It would qualify. It's big enough. It's round. It has its own magnetic field, something no other moon in the solar system can claim. It has a thin atmosphere, a crust of ice, and underneath all that, something scientists have chased for decades. An ocean. A hidden ocean that holds more water than all of Earth's oceans combined. But here's where it gets weird. Ganymede isn't just big. It's also weirdly quiet. It's dark, almost invisible to the naked eye, and it orbits the largest planet at about 665,000 miles away. That's almost 3 times the distance from Earth to the Moon. It takes 7 days and 3 hours to complete one loop around Jupiter. And because Jupiter is so massive, and because Ganymede is locked in a gravitational dance with 2 other large moons, Europa and Io, the whole system is chaotic. It's violent, it's unfamiliar, and that's why NASA is terrified to land there. B-roll. Animation of Ganymede orbiting Jupiter, then zooming into its icy surface. You see, an ocean underneath miles of ice is a dream for astrobiologists. It could rewrite everything we know about life, but it's also a nightmare for engineers. To reach that ocean, you'd have to drill through an ice shell estimated to be between 60 and 90 miles thick. That's like drilling through Earth's entire atmosphere twice. No one has ever built a drill that can survive that pressure, that cold, and that isolation. Not to mention the radiation. Jupiter's magnetic field traps particles and accelerates them to near light speed, creating a radiation belt around Ganymede that would fry electronics within hours. NASA has sent probes past Ganymede. Juno flew by in 2016 and again in 2021, snapping pictures, but landing? The agency has been cautious. They're planning the Europa Clipper mission and the Jupiter Icy Moons Explorer, or JUICE, led by the European Space Agency. But a lander, that's a different story. B-roll, footage of Jupiter's radiation belts, then a spacecraft attempting to land on an icy surface. Imagine trying to land a spacecraft on a surface that's constantly shifting, bombarded by radiation, where the ground beneath you might not even be solid. The ice on Ganymede isn't like the ice in your freezer. It's ancient, under immense pressure. It behaves more like a thick, slow-moving fluid than a solid crust. And if that crust cracks, and it does all the time, water from the hidden ocean rushes up through the cracks, creating giant geysers that freeze instantly into towering spires of ice. That's the landscape you'd be landing on. A place where the ground is alive, where the moon is actively trying to hide its secrets. And that, right there, is why we're so drawn to it. Because it's impossible. It is impossible, and yet, here we are, looking back over 400 years of human curiosity, trying to figure out how we got from a tiny speck of light in a telescope to a moon that might have a hidden ocean. The story of Ganymede begins, as so many cosmic discoveries do, with a man named Galileo Galilei. It was January of 1610, and Galileo had just pointed his brand new, barely adequate telescope at the night sky. He was looking at Jupiter, and he noticed something strange. 3 little stars were lined up next to the giant planet. A few nights later there were 4. What he was seeing, of course, wasn't stars at all. He was watching moons orbiting Jupiter, and that simple observation shattered the entire world. You have to understand the historical context. Back in 1610, everyone believed everything orbited the Earth. It was the geocentric model, neat and tidy, and it put us at the centre of everything. But Galileo's discovery of Ganymede, along with Io, Europa and Callisto, proved that not everything revolves around us. There were worlds orbiting another world. It was a direct contradiction to centuries of church doctrine and Aristotelian physics. Galileo was essentially pointing his telescope at the heavens and saying, "Look, you're wrong." It got him into a lot of trouble, but it also opened the door to modern astronomy. And yet, for the next 369 years, that's all Ganymede was. A dot of light. A little pinprick in the darkness that astronomers could track, measure and name, but never really see. It was just there, a silent witness to the centuries of science that followed, waiting for us to get a little closer. That wait ended in 1979. That's when NASA's Voyager 1 and Voyager 2 spacecraft on their grand tour of the outer solar system finally flew past Jupiter's largest moon, and what they saw, even from a distance, blew their minds. The Voyager images revealed a world that was literally two-toned. It wasn't just a uniform, boring lump of rock and ice. No, it was a patchwork. One part of the surface was dark, almost brownish-red, heavily cratered and ancient. Scientists call these dark areas the redunes. They are the oldest surfaces on the Moon, scarred by impacts from the very early days of the solar system. They look like old, wrinkled skin, bearing the marks of a violent past. But right next to these dark patches there were brilliant, bright white bands, like someone had taken a giant knife and carved grooves across the Moon's face. These are the Sulci. They are the young parts of Ganymede. They are bright, grooved, tectonic, and absolutely unlike anything we had ever seen on any other moon. The Voyager flybys gave us our first real glimpse of a surface in constant, violent flux. You had these old, dark highlands sitting right next to fresh, bright, ridged plains, as if the moon had been ripped apart and sewn back together at some point in its deep past. It hinted at something geologically complex, something that had been stretched, cracked, and flooded over and over again. The message from Voyager was clear. This wasn't a dead world. It had a story to tell, a story written in ice and rock, but it would take another 2 decades, and a much more ambitious mission, to even begin to understand what that story really was. Now let's talk about the surface, because honestly, that's where the truth starts to get really weird. When you look at Ganymede from a distance, it's not just a bland white ball of ice. It's a patchwork. You have these huge, dark, ancient regions, and then these long, brighter bands cutting through them like veins. That contrast isn't just for show. That darkness is history. Pure, unadulterated, 4 billion-year-old history. The dark regions are the oldest real estate in the outer solar system. Scientists call them the frozen archive for a reason. Imagine a parchment, but instead of ink, the story is written in impacts. Those dark plains are covered in craters upon craters. They are a direct record of the heavy bombardment period, that chaotic era when the solar system was still a shooting gallery. Every single one of those pockmarks is a fossil of a collision that happened before life even crawled out of the mud on Earth. It's a ledger of violence frozen in time. But here is where the geology gets really interesting, and a little bit spooky. You see, ice doesn't behave like rock over 4 billion years. It flows, it creeps, it relaxes. So an impact crater on Ganymede doesn't look like the crisp, sharp bowl you see on the moon. No. Over time, the ice slowly slumps back into the hole. The walls soften. The rim collapses. It creates a ghost of a crater. Scientists call this the palimpsest effect. Like an old manuscript that has been scraped clean and written over. The crater is still there, but it's a shadow of itself, a faint ring of light ice on a dark background. It's the whisper of an impact that happened when the solar system was young. And that brings us to the grooves. This is where the scale of the story shifts from simple history to epic upheaval. Those bright bands, the grooved terrain, they aren't just scratches. They are the scars of planetary destruction. We are talking about tectonic forces that rip the surface apart. Something pulled the crust open, creating massive troughs and ridges that run for thousands of kilometers. Some of these grooves are literally a kilometer deep. We are talking about mountain ranges of ice, folded and faulted. It's the most extensive tectonic terrain in the entire solar system. The only way you get that is if the interior of Ganymede was at some point incredibly active. Something churned deep below, and the frozen crust cracked under the strain. Now let's look at the conditions up there. It's cold. Really cold. We are talking about a surface temperature of negative 163 degrees Celsius. Let that sink in for a second. That's colder than any natural temperature ever recorded on Earth. That is the temperature at which gases like oxygen and nitrogen turn into solids. On Ganymede, the ice you are standing on is as hard as granite. It doesn't melt, it doesn't sublimate easily. It's a frozen fortress. And here is the paradox. The fact that it is so brutally cold on the surface, that the ice is so rigid, makes the idea of a liquid ocean underneath almost insulting to common sense. How can something that hot be hiding under something that cold? It seems impossible, but the math says it has to be there. The friction from tidal forces, the decay of radioactive elements deep in the rocky core, the sheer pressure of that crust. It all points to one inevitable conclusion. Down there, miles beneath your feet, it isn't cold, it's warm, it's liquid, it's moving. Think about the implications. A solid crust of ice as hard as rock on top, a potentially salty ocean sloshing around in the middle, and a rocky radioactive core down at the bottom. That's a structure we have seen before. That's the structure of a planet with a heartbeat. And that heartbeat is the mystery. Because if that ocean exists, and if it has been there for billions of years, then what exactly is swimming around in the dark? That is the question that keeps planetary scientists up at night. And it's the question that makes landing there the single most terrifying proposition NASA has ever considered. To answer that question, we first have to understand the single most insane fact about this moon. It is not the size. It is not the distance. It is the shell. We are talking about an ice crust that is 800 kilometers thick. Let that number sink in for a second. 800 kilometers. If you took the entire continental United States and stacked it on top of itself, you would barely reach the halfway point. This is not a snowball. This is a frozen world that could swallow entire mountain ranges whole without blinking. And for decades, we assumed it was just a solid, inert block of ice, but the truth is far stranger and far more chaotic. The first clue came from a spacecraft that is now a ghost. In the 1990s, the Galileo probe swung past Ganymede and made a very simple measurement. It measured the gravity. It measured how the spacecraft's trajectory wobbled as it flew by. And based on those tiny deviations, scientists realized something shocking. The ice shell does not have a uniform density. It is layered. It is, to put it simply, a parfait. You have layers of high-pressure ice, so compressed it behaves like a solid crystal. Then above that, a zone of slushy convective ice. Then a layer of liquid water trapped between the ice layers. Then on top, the cold, brittle crust we see from orbit. This is not a static block. It is an active breathing system of phase changes. Ice turning to liquid, liquid refreezing, crystals shifting under forces that would crush our deepest submarines in an instant. But here is the paradox. The thickness is the central problem. On the one hand, that shell is an immense insulator. Think of it like a blanket that is 800 kilometers deep. It traps heat from Ganymede's core, heat from radioactive decay, heat from the tidal flexing caused by Jupiter's gravity. That trapped heat is what keeps the subsurface ocean from freezing solid. Without that thick shell, the ocean would have turned to rock-hard ice billions of years ago. So the shell is the protector. It is the reason life might be possible down there. But here is the flip side. That same shell is an immense barrier. It is a prison. To get to that ocean, to touch that water, you have to drill through 800 kilometers of ice. And not just any ice. You have to deal with the high-pressure ice zones, which are harder than granite. You have to deal with the slush zones, which would swallow any drill bit like quicksand. You have to deal with the fractures, the cryovolcanoes, the zones where the ice is actively deforming under its own weight. This is the moment where NASA looks at this moon and says, we have a problem. To land on Ganymede is one thing. To land on a surface made of solid ice is difficult but possible. But to study that hidden ocean, to sample it, to find out what lives there, you have to go through that shell. And nobody has a plan for that. Not a credible one, because every meter you go down, the pressure increases. Every meter, the temperature changes. Every meter, you move further from the sun, further from your energy source, further from any hope of communication. The shell is a wall 800 kilometers thick, and we are standing on top of it with nothing but a hammer and a dream. So what does this mean for us? It means that Ganymede is a paradox. It is the most promising place in the solar system for finding a second genesis of life. But the very thing that makes it promising is also the thing that makes it inaccessible. The shell is both the key and the lock. And the most terrifying part is this. We have only seen a tiny fraction of it. The Galileo data gave us the broad strokes, but we do not know the details. Is there a liquid layer trapped between the ice phases? Potentially. Could that layer be constantly circulating, exchanging chemicals with the ocean below? Possibly. Could there be life living in the cracks of the ice itself, in those high-pressure zones? Nobody knows. And that is the true horror of Ganymede. It is not a dead world. It is an active, dynamic, hidden ocean. And we are standing on the roof, listening to the water move, but we cannot open the door. Not yet. Now, let's talk about the scale of this thing. Because when we say Ganymede has an ocean, we are not talking about a little puddle. We are not talking about something like Lake Superior, or even the entire Atlantic Ocean. We are talking about a volume of liquid water so staggering it breaks the human brain to visualize. The number is 1.4 billion cubic kilometers. That's billion with a B. To put that in perspective, Earth, our blue marble, the so-called water planet, has roughly 54 million cubic kilometers of water in all its oceans, lakes, rivers and glaciers combined. Ganymede's hidden ocean holds 26 times that amount. 26 times. If you could somehow scoop all that water out of Ganymede and spread it evenly across the surface of Earth, every single continent would vanish. Every mountain range, every desert, every city, every forest, gone. The entire planet would be submerged under a global ocean 2.7 kilometers deep. That's nearly 9,000 feet of water over your head, over the top of Mount Everest, over everything we have ever built or known. But here is where the story flips from a simple numbers game to something genuinely profound. Water is not rare in the universe. We find ice on comets, on moons, even on shadowed craters of Mercury. But liquid water, stable over cosmic timescales, in contact with a rocky seafloor, with chemical gradients, with tidal heating providing energy. That is the Holy Grail. And Ganymede has all of it, and it has had it for billions of years. This makes Ganymede the single largest reservoir of habitability in the entire solar system, excluding Earth itself. Think about that. Not Mars with its dried-up riverbeds and thin atmosphere, not Europa with its smaller, saltier ocean, not Enceladus with its geysers and tiny volume. Ganymede wins, by a landslide. The sheer volume of water, the pressure at the bottom of that ocean, the hydrothermal vents we suspect are active right now. All of it creates what scientists call a redox gradient, a chemical battery. Life as we know it runs on these gradients. You need a source of energy, a source of carbon, and liquid water. Ganymede has all three in spades. And here is the part that keeps planetary scientists awake at night. That ocean has been there for 4 billion years. 4 billion years of chemical mixing, of tidal flexing, of energy flowing through warm water vents. On Earth, life emerged within the first billion years. If the same rules apply, if the same cosmic lottery played out on Ganymede, then something has been swimming in that darkness for as long as life has existed on Earth. It could be nothing more than single-celled microbes clinging to rocks in the abyss, or it could be something more complex. We don't know, and we are terrified to find out. Not because of monsters, but because of the implications. If we find life there, it means life is common. It means we are not special. It means the universe is probably teeming with it. And if we don't find life there, with all that water and all that time, Then Earth becomes the lonely miracle. Either answer is devastating. But here is the kicker. We cannot even land on Ganymede yet. Not safely. Not without contaminating it with our own microbes. NASA has been working on a mission called the Europa Clipper, which will study Jupiter's other moon, Europa. But a dedicated lander for Ganymede is still a dream. The radiation around Jupiter is brutal. The distance is immense. The ice crust is thicker than we once thought, maybe 100 kilometers deep. Drilling through that is beyond our current engineering. So we listen. We measure its magnetic field. We watch its auroras. We calculate the tides. But the ocean stays hidden. It stays dark. And somewhere down there, in that vast, silent, crushing abyss, if anything is alive, it has no idea we exist. It is a startling fact. A cosmic oddity that sets this moon apart from every other one we have ever found. Out of the hundreds of moons in our solar system, Ganymede is the only one that generates its own magnetic field. Think about that for a second. Every other moon, from our own quiet, cratered Luna to the volcanic hellscape of Io, they are all magnetic ghosts passively drifting through the magnetic fields of their parent planets. But not Ganymede. Ganymede fights back. Deep inside its core, something is alive, something is churning, and it creates a magnetic bubble around itself that is entirely its own. This is not just a neat little fact for a textbook. This is a thunderous implication. For a moon to have a magnetic field, it needs a dynamo, and a dynamo requires a very specific kind of engine. You need a liquid, electrically conductive interior that is in motion. Here on Earth, that engine is our molten iron core, spinning and twisting, generating the shield that protects us from the worst of the solar wind. On Ganymede, the story is the same, but the scale is different. The evidence points to a liquid iron core, a heart of molten metal wrapped in layers of rock and ice. That is the engine, and that engine is still running. So, what does this mean for the ocean we have been talking about? It changes everything. This is not a dead moon with a frozen pocket of ancient water, a relic from a time long past. This is a geologically active world. That liquid core is a source of immense heat, a primordial furnace that has been burning for billions of years. That heat has to go somewhere. It radiates outward, travelling through the rock and up toward the surface. It melts the lower layers of the ice shell, keeping that hidden ocean from freezing solid. The magnetic field and the ocean are inextricably linked. The core provides the heat maintains the water, and the water, being salty, is electrically conductive, which in turn helps sustain the magnetic field. It is a self-perpetuating system, a cosmic feedback loop that has been running for eons. And we can see the proof of this system with our own eyes, or at least with the eyes of the Hubble Space Telescope. Ganymede, because it has its own magnetic field, creates a unique phenomenon. It carves out a little pocket of space inside the vast magnetic field of Jupiter, a moon within a magnetosphere, and in this pocket, charged particles from the Sun get funneled down toward the poles of Ganymede, just like they do on Earth, and when they hit the thin atmosphere, they glow. Hubble has seen it. It sees auroras, shimmering ribbons of ultraviolet light, dancing at the north and south poles of a moon 500 million miles away. Auroras are the visible signature of a magnetic field in action. They are the ghostly breath of that liquid iron engine, and they are telling us, as plain as day, that the engine is still running hot. This is where the stakes get raised to a level that keeps planetary scientists up at night. If the core is active, if the heat is flowing, then the ocean is not a static frozen-over puddle. It is an actively maintained environment. It is a system. You have a heat source at the bottom, a thick insulating blanket of ice on top, and a liquid layer of water in between. That is a recipe for chaos. That is a recipe for chemistry. On Earth, we find life in every single crack and crevice where there is water and a source of energy. We find it in the boiling vents at the bottom of the ocean, in the acidic hot springs of Yellowstone, and deep in the bedrock miles underground. We call these extremophiles, and they thrive on environments that would kill us in seconds. The ocean of Ganymede is not just a candidate for life, it is a perfect incubator for it. The heat from the core creates hydrothermal vents on the seafloor, spewing minerals and chemicals into the dark water. This is the same recipe that many scientists believe sparked life on our own planet. So there it is. The magnetic anomaly is the key that unlocks the whole mystery. It tells us that Ganymede is not a frozen corpse. It is a dynamic, living world. It has a beating, molten heart that sustains a vast, hidden ocean. And that ocean is warm. It is geologically active. It is chemically rich. It is the most promising place to look for alien life in our own backyard. And that is precisely why NASA is terrified to land there. Not because of some monster lurking in the darkness, but because of the terrifying implications of what we might find. The ocean is not a dead relic. It is a waiting engine for something we have never seen before. And if we are wrong, if we contaminate that pristine ancient environment with a single microbe from Earth, we will have destroyed the one thing we have been searching for our entire existence. That is the weight of the magnetic anomaly. That is the burden of discovery. Because here is the real secret. That ocean beneath Ganymede's crust isn't just a lucky accident. It is a forced, relentless, cosmic inevitability. And it all comes down to a brutal gravitational trap that Jupiter set for its 3 largest moons, a dance of pure, violent physics we call the Laplace resonance. Imagine 3 children holding hands and spinning in a circle. Now imagine that circle is not perfect, and every time one child slows down, the other 2 yank them forward. That is what is happening out there. Io, Europa and Ganymede are locked in an orbital resonance. For every single orbit Ganymede makes around Jupiter, Europa makes exactly 2 and Io makes exactly 4. This is not a coincidence. This is a celestial prison sentence. Because their orbits are not perfect circles, they are slightly elliptical. That means as these moons swing around Jupiter, they are constantly being pulled and stretched by the planet's immense gravity. But here is the twist. The resonance keeps their orbits from ever becoming perfectly round. Every lap they take, their distance from Jupiter changes, and that change creates friction. It creates heat. Imagine bending a metal wire back and forth until it burns your fingers. That is tidal heating. On Io, this effect is so extreme that the Moon is literally the most volcanically active place in the solar system, a world of continuous molten hellfire. On Europa, the heating is gentler, just enough to maintain a liquid ocean beneath its icy shell. But Ganymede sits in the sweet spot. Not too close, not too far. The tidal heating it receives is just enough to keep its internal ocean moving, to keep it from freezing solid into a block of ancient ice. You have to understand the false limit here. Most scientists assumed that a moon that far out with a size like that would be geologically dead. They thought the ocean had to be a relic, a leftover from billions of years ago that would have frozen by now. They were wrong. The Laplace resonance is the engine that refuses to die. It pumps energy into Ganymede's core, forcing convection in the mantle, churning that water beneath the ice. This is why the ocean exists. It is not a frozen corpse floating in the dark. It is a world kept alive by the constant invisible tug of its siblings. A hidden ocean, breathing from the gravitational squeeze of a gas giant and 2 neighbouring moons. That is the real trick. The ocean is not dying, it is beating. And that is what makes landing on it so terrifying. Because if you think the surface is hostile, just wait until you understand what is happening underneath. And that brings us to the most frustrating part of the whole Ganymede story. The comparison. Because ever since we started talking about subsurface oceans, one moon has stolen all the headlines. Europa. You know the one. The smooth icy ball with cracks running across it like veins. Europa is Ganymede's smaller, flashier cousin. It gets all the glory, all the funding, and all the dreams of alien life. But here is the thing nobody tells you. Europa is a trap. Europa's ocean is thinner. That is a fact. The ice shell above it might be only 15 to 25 kilometers thick in some places. That is practically a puddle compared to what Ganymede is hiding. So you would think, great, easier to drill through, easier to reach the water, right? Wrong, because Europa might have the shallowest ocean in the solar system, but it also has the deadliest real estate. Jupiter's radiation belt is absolutely merciless around Europa. We are talking about a surface that gets bombarded with enough radiation to kill a human in a matter of minutes. Not hours. Minutes. Any lander we send there would have its electronics fried, its instruments scrambled, and its mission lifespan measured in days, not years. It is a suicide mission dressed up in pretty scientific packaging. So that leaves us with Ganymede. Ganymede, where the ocean is deep and dark and terrifyingly far down. But Ganymede has a secret weapon, its own magnetic field. It is the only moon in the solar system with one. That magnetic field creates a bubble, a magnetosphere, that protects the surface from the worst of Jupiter's radiation. So the surface is safer, much safer. You could last weeks, maybe months, on Ganymede without getting cooked alive. But here is the devil's bargain. To get to that safe surface, you have to accept that the ocean below is buried under an ice shell hundreds of kilometers thick. Hundreds, not dozens. So the trade is simple. Do you want a thin ocean that will kill you from above? Or a thick ocean that you can never, ever reach from below? Two different types of inaccessibility. Two different flavors of impossibility. And that is the tension, that is the terror. We know the ocean is there. We can see the evidence in Ganymede's wobble, in its auroras, in its magnetic signature. But knowing something exists, and knowing how to touch it are two completely different games. Europa is the celebrity. Ganymede is the mystery. And right now we are standing on the edge of that mystery, staring down through 900 kilometers of solid ice, wondering how on Earth, or rather how off Earth, we are ever going to get through. That is the question that ends this episode. The ocean is real, the ocean is alive, but the path to it? That path might be the most terrifying challenge we have ever faced. And there it is, a hidden ocean locked away beneath a frozen shell for the better part of 4 billion years. Imagine that for a moment. No sunlight, no warmth, no surface waves breaking against a shore, just an endless silent abyss of liquid water, utterly alone in the dark. It has never seen the stars. It has never felt the touch of a single ray of light. It simply exists turning slowly in the blackness of space, completely unaware that we, a fragile species on a distant blue speck, even know it is there. That is the quantum of loneliness. A profound, almost terrifying isolation that makes you stop and think. Here is an ocean larger than all of Earth's seas combined, and it has never been touched. It has never been disturbed. It is the most pristine wilderness in the solar system, a time capsule of chemistry, and maybe, just maybe, life. We have mapped its gravity field. We have detected its salts. We have measured its immense tides, squeezed and pulled by Jupiter's crushing gravity. We are certain it is there, but the ocean itself does not know we are watching. It does not know that we have built machines that have flown for years just to glimpse its frozen lid. It does not know that soon we will stop looking from afar and start planning our descent. And that brings us to the question, the real question. The one that keeps planetary protection officers awake at night. What happens when we finally try to touch it? You realize, don't you, that this ocean might as well be on another galaxy. There's no shortcut here, no secret tunnel, no hidden crack in the armor. Between us and that alien ocean sits a wall, an 800-kilometer wall of solid ice. That is not a typo. That is not an exaggeration. 800 kilometers. To put that in perspective, the entire planet Venus is about 12,000 kilometers across. This ice shell is so thick it could swallow the Earth's entire atmosphere, oceans included, and still have room for more. When I say NASA is terrified, I do not mean they are scared in a dramatic Hollywood way. I mean they are professionally, coldly, analytically terrified. Because terror in space exploration is not about monsters. It is about limits. It is about the cruel arithmetic of energy and time and pressure. Picture it. You are standing on Ganymede's surface, your spacesuit performing heroically against the vacuum and the radiation. You look down, and at your feet, that pale, scarred ice stretches infinitely in all directions. Beneath you, 100 kilometers down, then 200, then 500, then 800, there is water. More water than all of Earth's oceans combined, sloshing around a metallic core, generating its own magnetic field. But you cannot see it. You cannot smell it. You cannot drill for it. Not with today's technology. You could land a nuclear-powered probe, set it on the ice, and let it melt downward for a year. How far would it go? Maybe a single kilometre, maybe 2. At that rate, it would take 400,000 years to reach the ocean. Not months, not decades, 400,000 years. This is the problem. The most exciting ocean in the solar system sits behind a door that is 800 kilometres thick, and we do not have the key. We have theories. We have hopes. We have whispered conversations about cryobots and nuclear-heated submarines that could eat through ice like a worm through an apple. But those are still just drawings on whiteboards. Right now, the ocean of Ganymede remains completely and perfectly inaccessible, and that is what keeps people up at night. Not the fear of what we might find, but the fear that we might never get there at all. So, why aren't we already there? It's not for lack of wanting. It's because Ganymede is practically screaming at us to stay away. The problems form an unholy trinity of barriers, 3 massive obstacles that seem designed to keep humanity out. Let's talk about the first one, the ice. Not a cute frozen lake, a crust of water ice that averages 1,000 kilometres thick. That's a wall of ice the size of a small continent. Our best drills can barely punch through a few kilometres of rock on Earth. Oil rigs go maybe 12 kilometres deep, but they're tiny, fragile machines operating in a warm, protected environment. On Ganymede, you have to drill through 1,000 kilometres of ice that's as hard as granite in some places and as unpredictable as slush in others. You have to do it without the drill freezing solid, jamming, or exploding from pressure. No current drill can do this job, not even close. But let's say you solve that. You invent a drill that chews through ice like a hot knife through butter. Now you have to survive the landing itself. That brings us to problem 2, radiation. Jupiter's magnetic field is the strongest in the solar system. It traps particles from volcanic moon Io and accelerates them to insane speeds. The result is a radiation belt that makes Chernobyl look like a sunny day at the beach. Ganymede sits inside this hellscape. The surface is blasted with doses that would kill a human in hours, maybe minutes. It fries electronics. It degrades metals. It turns delicate instruments into useless scrap. Every lander near Jupiter must be hardened with tons of lead and shielding just to survive a few weeks. But shielding is heavy. Heavy costs money. Heavy means a bigger rocket. A bigger rocket means a bigger budget. It's a vicious cycle. Then there's problem 3, the power deficit. Ganymede is 5 times farther from the Sun than Earth. Sunlight is incredibly weak. At that distance, solar panels would need to be the size of a football field just to power a single small probe. And you're fighting the cold. Electronics need warmth to function. Warmth uses power. Power is exactly what you don't have. So you're stuck with nuclear batteries, radioisotope thermoelectric generators, or RTGs. They work and are reliable, but they're expensive, heavy, and hotly debated for safety. Even an RTG has a limited lifespan, so you have 1,000-kilometre ice crust to drill through, a lethal radiation environment to survive, and almost no energy to do any of it. That's the unholy trinity, and it's why right now we have more questions than answers. But let's get real for a second. Even if you somehow solved the power problem, even if you managed to shield your probe from Jupiter's radiation belt long enough to get it to the surface, you're still faced with what might be the single most humiliating engineering failure in the history of space exploration. You have to drill. You have to drill through an ice shell that is not a few meters thick, not a few kilometers thick, but something like 800 kilometers thick. That is not a typo. 800 kilometers of solid ice. Think about that number for a moment. The deepest hole humanity has ever dug on Earth is the Kola Superdeep Borehole in Russia. You might have heard of it. It took them 20 years of drilling, non-stop, using the most advanced industrial machinery the Soviet Union could throw at it. And they managed to reach exactly 12.2 kilometers. That is 0.015% of the depth we would need to drill on Ganymede. 0.015%. And on Earth, we had gravity working for us. We had a stable platform. We had unlimited power from the grid. We had a team of engineers living in a town nearby, ordering spare parts, fixing broken drill bits, pumping drilling mud. We had all of that, and we still barely scratched the surface of our own planet. On Ganymede, you have none of that. But the depth isn't even the worst part. It's the pressure. At the base of that ice crust, where the ice finally gives way to liquid water, the pressure reaches over 1 gigapascal. That is roughly 10,000 times the atmospheric pressure at sea level on Earth. 10,000 times. For context, the pressure at the bottom of the Mariana Trench, the deepest point in our oceans, is about 1,000 times Earth's atmosphere. So we are talking about an order of magnitude beyond that. At those pressures, ice behaves strangely. It doesn't just melt. It can form exotic high-pressure phases, crystal structures that are denser and harder than anything a mechanical drill bit could possibly chew through. Even diamond-tipped tools fail under those conditions, because the ice itself becomes something closer to rock. And you have to imagine that your drill is not spinning in a warm, lubricated hole. It is grinding against a material that wants to squeeze it into a paste. The torque required to turn a drill string 800 kilometers long under that pressure is beyond any known engineering. The sheer mass of the drill string alone, if you built it out of the strongest titanium alloys we have, would snap under its own weight long before it reached even 10% of the way down. You simply cannot push a rod through 800 kilometers of ice. It's not a question of money, it's a question of physics. So what about melting? Instead of drilling mechanically, could you just melt your way down, like a hot knife through butter? That's the idea behind cryobots, probes that use heat to liquefy the ice in front of them and sink through. It sounds elegant. But here's where the heat budget becomes a nightmare. To melt through that much ice, you need energy to raise the temperature of the ice from its ambient surface temperature, around minus 160 degrees Celsius, all the way to the melting point. And then you need the latent heat of fusion to actually turn that ice into water. The numbers are staggering. For a probe the size of a small car, you would need roughly the energy equivalent of detonating a small nuclear warhead. But you have to release that energy slowly, continuously, over months or years, inside a sealed cryobot that cannot radiate heat into a vacuum because it's surrounded by solid ice. The waste heat has nowhere to go except into the ice you're melting, so that part is actually efficient. But the initial power source is the problem. You cannot carry that much energy in batteries. Even the most advanced RTG, like the ones powering the Voyager probes, puts out a few hundred watts. That's not enough to melt a cubic meter of ice in a reasonable time. You would need something like a compact nuclear reactor, the kind we have on nuclear submarines, but scaled down to fit inside a spacecraft. And we have never, not once, launched a nuclear reactor into space. The political, safety and technical hurdles are immense. Even if you could, the weight would be prohibitive. So you are stuck. You cannot drill. You cannot melt. You cannot even get started. This is why, despite Ganymede being arguably the most compelling ocean world in the solar system, the words beyond any known engineering are the quietest truth behind every NASA proposal. And that is a terrifying place to be, because the ocean is there. We know it is there. We just have no idea how to reach it. Nothing about this world is safe. The ocean beneath Ganymede might hold life, might hold answers to questions we have barely learned how to ask. But the path to that ocean runs straight through hell, and hell in this case is invisible. It is silent. It does not burn with fire or glow with warning lights. It simply kills. It is radiation. Jupiter does not just sit there as a pretty striped giant in our night sky. Jupiter is a monster. Its magnetic field is the largest single structure in the entire solar system, stretching out for millions of miles, trapping particles accelerated to nearly the speed of light. Think about what that means. Every second, the giant planet's rotation whips charged particles around like a cosmic blender, creating radiation belts that would make a nuclear reactor look like a nightlight. These are not the gentle Van Allen belts that wrap around Earth. These belts are brutal, relentless, and designed by nature to shred anything that dares to enter them. Ganymede swims right in the middle of this storm, and that is where our problems truly begin. Let me tell you about the Galileo spacecraft. NASA sent Galileo to Jupiter back in the late 1980s, and it arrived in 1995. It was a masterpiece of engineering, a robotic explorer built to withstand things most machines could never survive. And it did survive for a while. But the radiation belts of Jupiter did not care about human ingenuity. They wore Galileo down, year after year. Its electronics suffered glitches, memory errors, and performance degradation. The spacecraft adapted, overcame, kept fighting, but the damage was permanent. By the end of its mission, Galileo had absorbed enough radiation to cripple lesser spacecraft entirely. And here is the kicker. Galileo was not even trying to land on Ganymede. It was just flying by at a safe distance, and it still got hammered. Now imagine sending a lander down to the surface, where the radiation is far worse. That is a different game altogether. Ganymede does have one advantage, and it is a strange one. It is the only moon in the entire solar system that generates its own magnetic field. That field creates a tiny bubble of protection, a weak shield that deflects some of the harshest radiation from Jupiter. But do not let that comfort you. The shield is laughably thin compared to what we have on Earth. It does not stop the high-energy particles, it just slows them down a little. It is like wearing a paper hat in a hurricane. Sure, you might feel slightly better, but the storm is still going to tear you apart. Now, here comes the truly terrifying number. Engineers have looked at the data, run the models, and realized something that keeps them up at night. To survive on the surface of Ganymede for more than a few weeks, any electronics we send must be hardened to withstand roughly 100 times the radiation dose of anything currently used in space exploration. 100 times. The most radiation-hardened components we build, designed for deep space missions, nuclear environments, military satellites, they are not enough. We would need to invent entirely new materials, new shielding technologies, new ways of building circuits that do not exist yet. And even then, the timeline would be tight. What about a human? Let us paint that picture for a moment, because it matters. If an unprotected astronaut stepped onto the surface of Ganymede, they would receive a lethal dose of radiation in less than a single day. Not a month, not a week, a day, and it would not be a peaceful passing. It would be violent cellular destruction, nausea, vomiting, fluid loss, blindness, failure of the bone marrow, and ultimately death. The brain would shut down as radiation ripped through DNA like a chainsaw through paper. That is the reality of this invisible killer. It does not care about ambition. It does not care about the beautiful ocean waiting just beneath the ice. It only cares about stopping us. And so far, it is winning. The radiation problem is a nightmare, yes, but let's be honest with ourselves. Even if we somehow solve that, the surface itself is a monster of a different kind. Ganymede doesn't want visitors. It has made that abundantly clear. And the moment you try to land a spacecraft there, you realize you aren't just battling an invisible killer from above. You're fighting the ground beneath your feet. First, let's talk about gravity. Or rather, the lack of it. Ganymede has only about 14.6% of Earth's gravity. That means, if you could stand on its surface, you'd feel like you weighed less than a bag of groceries. Now, imagine trying to land a speeding spacecraft in that environment. You can't just slow down gently. You have to execute a precise, terrifying ballet of thrusters. And the problem is, when you fire those thrusters in low gravity, you kick up dust. But not just any dust. This is fine, organic-rich dust. It hangs around, it lingers, it floats in the vacuum like a slow-motion cloud of hell. That dust can blind your sensors, clog your instruments, and ruin your landing before you even touch the ground. It's not a surface, it's a trap of flying grit that doesn't want to settle. Then there's the ice. You hear the word ice and you think of a skating rink, something solid and predictable. Not on Ganymede. The surface here is a chaotic mixture of ancient fractured ice and rock. Some of it is as hard as concrete. Some of it is structurally unstable, like a snowdrift hiding a 10-foot crater. You have craters everywhere, overlapping each other. You have that famous groove terrain, these massive tectonic ridges that slash across the surface like scars. Finding a flat, safe landing site is like trying to find a clean piece of floor in a garbage dump. Every potential spot looks good from orbit, but up close, it's a minefield of ridges, cliffs, and loose debris. You set down one leg on stable ice, the other leg on a patch of dust that gives way, and your multi-billion-dollar spacecraft tips over. Game over. And remember, there is no atmosphere. None. Zero. So parachutes? Forget about them. They are useless here. You cannot glide down. You cannot use aerobraking. The only way to slow down is with pure, brutal propulsive braking. That means your engines have to fire hard, right until the moment of touchdown. That burns fuel like crazy. It reduces your payload, and it puts you on a razor-thin margin of error. One miscalculation in the thrust angle, one subtle shift in the dust plume, and you impact the ice at a speed that turns your lander into confetti. So here is the terrifying truth. The ocean beneath Ganymede might be the most promising place for life in our solar system, but the surface is engineered by chaos to keep us away. It's low gravity, it's dust that won't settle, it's ice that lies to you, and it's a navigation nightmare with no atmosphere to help. For the engineers back on Earth, this is the gates of hell. They dream of that ocean, but they have to build a machine that can survive a landing on a world that seems to hate the very idea of visitors. And frankly, every time they run the simulations, they get a little more nervous. And this is where the scale of the problem really starts to mess with your head, because we aren't just talking about a tough landing zone. We are talking about the brutal, crushing reality of distance. Let's put some numbers on that for a second. The signal from a spacecraft on Ganymede has to travel, on average, somewhere between 32 and 52 minutes just to reach Earth, one way. That means if the lander sends a message that says, "I am tipping over," it takes over half an hour for that cry for help to arrive. And then, once the engineers back at the Jet Propulsion Laboratory scramble, they send a command back. That's another half-hour trip. So you're looking at over an hour between a problem occurring and a solution being received. That is not remote control. That is a joke. You cannot drive a car with a 60-minute delay on the steering wheel. You would be in a ditch before you even thought about turning. Now, think about the Perseverance rover on Mars for a moment. Mars is already a nightmare to operate. It's a 20 light-minute round trip. Rover drivers on Earth have to plan each drive like a chess match because you can't react to a rock in the road. You just have to trust the software to handle it. And even then, Perseverance needs constant supervision. But Ganymede? That is not 20 minutes. That is 60 or even 100 minutes of silence. Imagine sending your kid off to school on a bus that takes an hour to get there. But you also have no phone, no way to know if they made it until after they've already failed. That is the level of terror we are talking about. The lander cannot just be smart. It has to be godlike. It needs an artificial intelligence so advanced, so autonomous, that it can make decisions about its own survival in real time, without waiting for permission from Earth. It needs to see a boulder field, calculate a new landing site, adjust its trajectory, and execute the entire maneuver before the first light from that boulder field even reaches us. But here is the kicker, the part that makes NASA's engineers wake up in cold sweats. It is not just the constant delay. There is something worse, something called solar conjunction. Every so often, the sun gets in the way. It sits directly between Earth and Jupiter. And when that happens, the sun blasts out so much electromagnetic noise that all communication becomes impossible. For weeks, 3 weeks, 4 weeks. The lander goes completely dark. No signal in, no signal out. You are not just operating blind, you are operating deaf. The vehicle is completely isolated, floating in the blackness of the Jovian system, with no one to help it, no one to talk to, and no way to know if it is even alive. That is not a mission, that is a prison, a light-speed prison. And the only way to survive that prison is to build a machine that is comfortable being alone. That is not afraid of the silence, that knows exactly what to do when the universe goes quiet. Because when that conjunction ends and the first faint signal finally squeaks back through the static, the engineers on Earth will be holding their breath, praying that the mind they gave it was enough to keep it alive. But let's talk about the real nightmare. Not the cold, not the radiation, not even the alien ocean itself. The real nightmare is the price tag, and this is where the whole dream starts to crack. The Europa Clipper mission, which is already considered astronomically expensive by most standards, cost roughly $5 billion. That's $5 billion for a flyby mission, a spacecraft that will never touch the surface, never drill through the ice, never taste the water. But a Ganymede lander? A mission designed to actually set down on that frozen crust, punch through miles of ice, and send a probe into the subsurface ocean? That's a whole different beast. We're talking $15 to $25 billion, and that's the optimistic estimate. If you know anything about how NASA budgets work, you know the final number is always double the initial pitch. So now you're looking at a mission that could easily swallow $30 to $50 billion of taxpayer money. Let me put that in perspective. That is more than NASA's entire annual budget. The whole agency, every Mars rover, every asteroid mission, every deep space observatory, all of it, everything they do in a single year, gone, just to see what lives under the ice of one moon. And if you think the James Webb Space Telescope was a financial disaster, you haven't seen anything yet. Webb started as a $1 billion project and ballooned to nearly $10 billion, causing years of delays and political headaches. Lawmakers still bring that up in hearings. They wave that price tag around like a weapon. And Webb actually delivered. It gave us images of the early universe. It produced science that made headlines. It had a clear, tangible payoff for the public. A Ganymede lander? What does it give us? Maybe worms. Maybe slime. Maybe a few blurry images of something that looks like a shrimp swimming in the dark. And absolutely zero benefit to life on Earth. No cure for cancer. No solution to climate change. No new iPhone technology spinning off from the engineering. Just knowledge. Pure, expensive, hard-won knowledge about a frozen ocean 600 million miles away. And that, my friends, is the true limit. Not the engineering, not the radiation, not the ice. Money. Congress has no appetite for a $30 billion mission that produces nothing but a few biology papers and some fuzzy pictures of alien microbes. They want return on investment. They want jobs in their districts. They want something they can hold up at a press conference and say, look what we did for the American people. A deep sea dive into a moon of Jupiter. That's a tough sell when voters are worried about the price of groceries. The political reality is brutal. The science community could scream until they're blue in the face about the importance of finding extraterrestrial life. But unless that life comes with a patent and a commercial application, the checkbook stays closed. So, here's the cold truth. The miracle of discovering life in Ganymede's ocean might already be out there, swimming in the dark, waiting for us. But the price to reach it is so staggering that we might just decide to leave it waiting forever. The universe is full of miracles. The question is whether we can afford to open the package. And that brings us to the single greatest roadblock in the whole mission. Actually, it's not a technology problem. It's not a funding problem. It's an ethical rule we made up. A self-imposed wall we built around the solar system. It's called planetary protection, and it's arguably more terrifying to NASA than the radiation on Ganymede's surface. Because this fear isn't about what we might find. It's about what we might bring with us. There's an international body called COSPAR, the Committee on Space Research, and they've written a pretty strict set of guidelines. If you want to send a lander to a place like Ganymede, you cannot just slap a heat shield on a washing machine and hope for the best. No, that spacecraft has to be sterile, I mean surgically impossibly sterile. Every screw, every wire, every square inch of the circuit board has to be baked, scrubbed, and zapped until there isn't a single living microbe left. Because here's the paradox that keeps astrobiologists up at night. If we send a dirty lander to the ocean world, and that lander finds something that looks like life, we have no way of knowing if it's actually a Ganymedian organism or just a stowaway from Cape Canaveral that survived the trip. It's the ultimate contamination nightmare. We'd be looking at the first contact with alien life, and it would be a complete lie. We'd have ruined the evidence. This isn't just theoretical hand-wringing. We've done it before on purpose to protect other worlds. Think about the Cassini spacecraft. When it ran out of fuel after nearly 20 years orbiting Saturn, NASA didn't just let it drift away. They made a deliberate choice. They crashed Cassini into Saturn's atmosphere, burning it up in a final fiery plunge. Why? Because one of its moons, Enceladus, has a subsurface ocean, just like Ganymede. And if Cassini had crashed there, the Earth bacteria hitching a ride on its old electronics might have contaminated that pristine ocean forever. So we sacrificed $1 billion spacecraft to keep the outer planets clean. We are that paranoid. But here's the dirty little secret. Planetary protection is a false limit. It's a rule built from fear, not from physics. The real cost isn't the sterilization process. It's the psychological barrier. If we ever decide that the risk of contamination is worth the reward of discovery, that wall comes down. Think about it. If we accept that we might accidentally seed Ganymede's ocean with Earth microbes, or that we simply cannot prove whether we did or didn't, then the mission becomes suddenly, terrifyingly possible. The whole block is self-imposed. So the question isn't just can we build a spacecraft tough enough to survive the ice crust. It's are we brave enough to lie to ourselves about what we might find? Because if we go and we find nothing, we'll always wonder if it was empty from the start, or if we just scared it away. But here's where the fantasy hits a wall of cold, hard math. You can dream up the perfect lander. You can armour it against radiation, insulate it against the cold, and even find a way to melt through miles of ice. But you cannot bend the laws of orbital mechanics. And that, right there, is the trap that keeps NASA up at night. Let's talk about the launch window problem. It sounds boring, I know. It sounds like something an engineer mutters over a spreadsheet. But in reality, it's the single most terrifying constraint in all of deep space exploration. If you want to get to Ganymede, you can't just point your rocket at Jupiter and fire the engines. That would take a ridiculous amount of fuel. No, you have to play a game of celestial pinball. You need gravity assists from Earth, Venus, and sometimes Mars to slingshot your spacecraft outward, gaining speed without burning every last drop of propellant. And that means the planets must be perfectly aligned. Not kind of aligned, perfectly. The European Space Agency's JUICE mission, launched in 2023, won't arrive at Jupiter until 2031. Think about that for a second. It takes 8 years just to get there, and that's with a carefully choreographed series of flybys, using the gravity of Earth and Venus to build up momentum. If you miss that launch window by even a few days, the planets scatter. The cosmic clock resets, and you're looking at a delay of 6 to 13 years before the next viable opportunity opens up. 6 years. Because of a missed Tuesday. This isn't a scheduling conflict you can solve with overtime or a second shift. It's a hard, immutable law of physics. The orbits of the planets are what they are. They don't care about your budget. They don't care about your political will. They don't care if you have the most brilliant landing concept. In human history, sitting on a launch pad in Florida, if the alignment isn't right, you wait. And in the world of space exploration, waiting that long isn't just an inconvenience. It's a death sentence for the program. Funding dries up, engineers retire, priorities shift. A 6-year delay can turn a flagship mission into a cancelled footnote. So why is NASA terrified? Because even if they solve every single riddle of the ice crust, even if they invent a lander that can withstand the crushing pressure and the radiation hellscape, they still face this brutal truth. We only get one shot every decade or so. There are no do-overs, no quick repairs. You don't send a rescue mission to Ganymede. You send your best, you cross your fingers, and you pray that the cosmos is feeling generous on that one specific Thursday in 2030-something. And if it's not, you don't just lose a spacecraft. You lose an entire generation's worth of scientific ambition. That's the trap. The window is open, but only just. And so, we find ourselves standing here, staring up at a world we can barely touch. A place where the single greatest discovery in modern astronomy, a liquid ocean, warm and salty, hidden beneath 100 miles of ice, sits just out of reach. And the thing that should terrify us isn't the radiation. It isn't the crushing pressure or the impossible engineering. It's the time. This isn't a sprint. It's not even a marathon. This is a relay race where you hand the baton to your children, and they hand it to their children, and you pray that somewhere down the line, someone crosses the finish line. We talk about launching a mission to Ganymede like it's a routine Tuesday, but the cold, hard truth is that from drawing board to splashdown, this kind of project takes decades. Not years, decades. By the time a probe touches that icy surface, the scientist who dreamed it up might be retired, or gone. The engineers who built it might be showing their grandchildren pictures of the launch. And that's the quiet terror here, isn't it? It's not the fear that we'll fail. We've failed before, and we've gotten back up. No, the real fear is that the answer, the proof of life, the confirmation of a second Genesis in our own cosmic backyard, might take a full century to get. 100 years of waiting, 100 years of funding cycles, of political shifts, of wars and recessions and changing priorities. Can you imagine the patience that requires? The kind of faith that says, I won't see this in my lifetime, but I'm going to do it anyway. That's the burden of the explorer. You build a monument to curiosity that you yourself will never stand beneath. You send a message in a bottle across a sea of time, hoping that someone, somewhere, will be there to read it when it finally washes ashore. And you do it because the alternative, ignoring that hidden ocean, turning our backs on the one place in the solar system that might hold the answer to "Are we alone?" That's simply unacceptable. So here we are, stuck between our ambition and our mortality. The clock is ticking. The window is open, but only just. And the ball, as always, is in our court. Ganymede is waiting. Silent, patient, hidden. But can we wait for it? The ocean is there. It has been there for 4 billion years. If life is inevitable, it's already there. So what does it look like? We ask this question not as scientists hunched over microscopes, but as explorers standing on the shore of the unknown. Because when you peel back the ice crust of Ganymede, you are not just finding water. You are finding a world that has been brewing something for longer than life has existed on Earth. Longer than the dinosaurs. Longer than the first single-celled organisms crawled out of our own primordial soup. That fact alone should make your skin crawl. Think about it. On Earth, life found a way in the most hostile places imaginable. Boiling vents at the bottom of the Pacific. Acid pools in volcanic craters. Frozen deserts in Antarctica. If life can squeeze into those cracks, what has it been doing for 4 billion years in a dark, pressurized ocean bigger than every ocean on Earth combined? The pressure down there is crushing. The temperature hovers just above freezing. The only light comes from radioactive decay, or the faintest gravitational friction. It is a world of eternal midnight, and yet that is exactly where we should be looking. NASA knows this. They know that if there is even a microscopic biosphere swimming in that abyss, it changes everything we think we know about life in the universe. But here is the terrifying part. They are scared to touch it, not because of the radiation, not because of engineering challenges. They are scared because if they land there, they might contaminate it. One stray bacteria from Earth could destroy a 4 billion-year-old ecosystem before we even get a glimpse. We could be the very extinction event we are trying to avoid. So we stare at the data, we build models. We imagine an invisible biosphere teeming with strange creatures we will never see, and we wait, because the worst thing we could do is rush in blind. The ocean is there, it is alive, or it was, or it could be, and we are stuck here, wondering if we will ever be brave enough to find out. So we have our checklist. 3 things. The minimum requirements for life as we know it. First, liquid water. We've confirmed that. Ganymede's ocean is buried under an ice shell hundreds of miles thick, but it's there. More water, in fact, than all of Earth's oceans combined. That's not a guess. That's data from the Galileo and Juno missions. Second, chemical energy. We think it's there. We know the ocean floor is likely in contact with a rocky mantle, and where you have rock and water together, you get chemistry. You get hydrothermal vents, maybe, like the ones on Earth where life thrives in total darkness. And third, a stable environment also confirmed. This is the weird part. Earth's early oceans were a chaotic mess, Meteorites, volcanic eruptions, shifting continents. Ganymede's ocean has been sitting there, protected under miles of ice for billions of years. It's the most stable home for life in the solar system. Maybe the universe. Think about that. We spend so much time searching for life on Mars or Venus, but those places are hostile in the extreme. Ganymede offers something different. A quiet, dark, pressurized world where conditions barely change. It's a perfect laboratory, not just for finding life, but for understanding what life really needs to start. The question we should be asking isn't just could life exist there, but has it already evolved into something we can't even imagine? Something that breathes sulfur instead of oxygen? Something that uses the planet's magnetic field instead of sunlight? The truth is, we have no idea. And that's exactly why NASA is terrified. Because if life is there, and if we send a lander, we could contaminate it. We could bring Earth bacteria into that pristine ocean and destroy a billion-year evolution in a single moment. Or worse, we could bring something back. Something that doesn't play by our rules. Something that has evolved in isolation for so long it might not even share our biology. But here's the thing. We also can't just sit here forever. The ocean is calling. It's the closest thing we have to a second Genesis, and every day we delay, we lose the chance to study it before our own probes, or someone else's, mess it up. So we build the models. We imagine the invisible biosphere teeming with strange creatures we'll never see. And we wait, because the worst thing we could do is rush in blind. The ocean is there, it's alive, or it was, or it could be. And we're stuck here, wondering if we'll ever be brave enough to find out. But at least we know right now that the minimum requirements are met. That's not just a theory, that's the most profound discovery of our generation. A world where life could exist, right under our noses, waiting. We've spent so long staring up at Ganymede, trying to calculate the thickness of its ice, trying to measure the saltiness of its buried sea. We talk about it like it's a puzzle, a piece of engineering, a problem to be solved. But we forget what we're really asking. We're asking if something, anything, could live down there in the crushing dark. And to answer that, we need to look at the most stubborn, the most unkillable, the most shocking forms of life our own planet has ever produced. Because if life can exist here in these absolute hellholes, then Ganymede starts to look less like a frozen rock and more like a welcome mat. Let's go back, way back, to 1977. A manned submersible called Alvin from the Woods Hole Oceanographic Institution is drifting over the Galapagos Rift about 1.5 miles deep. The team expects to find a barren, cold, dead plain. That's what deep-sea exploration taught them. Nothing lives down there without sunlight. It's a law of biology. Well, Alvin's cameras flicker on, and what they see is a shimmering ghost town. Towering mineral chimneys, belching black smoke and life. Piles of giant tube worms, red plumes waving, clams the size of dinner plates, blind white crabs scuttling everywhere. It was a city. An entire ecosystem, totally independent of the sun. The discovery shattered everything we thought we knew. How do you get energy without sunlight? You don't eat plants. You eat minerals. You eat the earth itself. This is where we meet the chemolithotrophs. It's an ugly word, but it describes something beautiful. Chemo for chemical, litho for rock, troph for feeder. Rock eaters. These bacteria don't need organic matter. They breathe in hydrogen sulfide, that rotten egg gas that would kill you as instantly, and they oxidize it to get energy. They pull carbon straight out of the carbon dioxide in the water. They build their bodies from the toxic soup of a volcanic vent. They are the ultimate recyclers, turning poison into fuel, and they are the only reason those giant tube worms exist. Every worm has a belly full of these bacteria, a symbiotic furnace. The worm provides a safe house, the bacteria provide the food. It's a partnership born in absolute darkness. Now extrapolate that to Ganymede. We think its ocean is salty, probably rich in minerals leached from the rocky mantle. We think there might be hydrothermal vents on the seafloor, similar to the ones on Earth. If there are, then the chemical energy for chemolithotrophs is there. The recipe is available, but that's just one ingredient, because the cold is a killer. The ocean on Ganymede is not a warm bath. It's hovering somewhere around the freezing point of fresh water, but under immense pressure it stays liquid. So any life down there would need to be a psychrophile, a cold lover. These are organisms whose cell membranes are packed with unsaturated fatty acids to stop them from turning into fat trees. Their enzymes don't freeze solid. They whip around in the cold like they're on a sugar rush. We've found psychrophiles in the Antarctic sea ice, living in brine channels that are barely above -20 degrees Celsius. They grow slowly, they live slowly, but they thrive. But this is where it gets truly personal. This is where we find the archetype for a Ganymedian microbe. There's a critter, a very special critter, with a name that sounds like a magic spell. Candidatus desulphurudis audaxviator. Audaxviator means bold traveller in Latin, and it was discovered 2.8 kilometres underground in a gold mine in South Africa. It lives in total isolation, no sunlight, no oxygen, no contact with the surface world for millions of years. It doesn't rely on any other species. It's a single-species ecosystem. It feeds on hydrogen and sulfate from the surrounding rock. It uses radioactive decay from uranium in the ground to split water molecules. It fixes its own nitrogen. It makes its own vitamins. It is a self-contained, self-replicating unit of pure resilience. A single bacterium living for millions of years in a pocket of water that hasn't seen the sky since before humans walked upright. Think about that. This bold traveller doesn't need a community. It doesn't need a host. It doesn't need a food chain. It just needs a little bit of water, a little bit of hydrogen, a little bit of sulfate, and a lot of time. It reproduces once every few hundred years maybe. But it's there. It's alive. It is the loneliest, most stubborn life form we have ever found. Now, let's put it all together. Ganymede has a global ocean. That ocean has a rocky seafloor. That seafloor likely has hydrothermal activity. That activity produces hydrogen, sulfur compounds, carbon dioxide. The exact menu for a chemolithotroph. The temperatures are extreme, but psychrophiles prove that cold is not a barrier, it's just a preference. And then there is the audaxviator. Proof that life can exist completely alone, utterly isolated, feeding on rock and radiation, in a dark that hasn't changed in geological epochs. It doesn't need a sun. It doesn't need a surface. It just needs a safe, stable, chemically rich crevice in the deep. And Ganymede offers that on a planetary scale. So when we say we're looking for life, we are not looking for a fish. We are not looking for a whale. We are looking for a single, microscopic, bold traveller, a slow, cold, patient rock-eater, floating in the darkness of an alien sea, its entire universe the chemical gradient around a vent. And we have the template for that life right here, in our own minds, in our own deep-sea vents, in our own Antarctic ice. The question is no longer whether life could theoretically exist there. The question is whether we have the guts to go down there and find it. Because if audaxviator can survive 2.8 kilometres underground in a South African mine, then somewhere in the silence beneath Ganymede's ice, something is probably alive, and it's been waiting for us. So we have a world with an ocean. We have energy, we have water, and we have a reason to believe life could actually exist there. The question is whether we have the guts to go down there and find it. Because if audaxviator can survive 2.8 kilometres underground in a South African mine, then somewhere in the silence beneath Ganymede's ice, something is probably alive. And it's been waiting for us. But here is where things get weird. And I mean genuinely, scientifically terrifying. Because we've been talking about this ocean like it's sitting on top of a nice, solid, rocky seafloor, just like here on Earth. You know, the kind of seafloor where hydrothermal vents can form, where heat from the planet's core can mix with water and create those rich chemical soups that life loves so much. But what if the bottom of that ocean isn't rock at all? What if it's ice? Not the kind you put in your drink. We are talking about high-pressure ice. Ice so dense and so compressed by the sheer weight of the ocean above it that it behaves more like a solid mineral than anything you'd ever call frozen water. This is the paradox at the heart of Ganymede. It's called the sandwich model. On top, you have a thick crust of normal water ice, maybe 150 kilometers deep. Below that, a liquid ocean probably around 100 kilometers thick. And then, below the ocean, you don't get rock. You get another layer of ice. But this layer is different. This is the high-pressure stuff, Ice VI and Ice 7. It could be hundreds of kilometers thick, pressing down on whatever is left of Ganymede's rocky core. If that is true, then the ocean floor is not basalt. It is not volcanic. It is a smooth, cold, crystalline ceiling of compressed ice. And that changes everything. Because if there is no rocky floor, there are no hydrothermal vents. And without vents, you lose the most obvious source of chemical energy for life. No black smokers, no warm seeps, no hot water bubbling up through cracks in the seafloor. That is a much less hospitable scenario. You essentially have a cold, dark ocean suspended between two layers of ice, with no direct connection to the planet's interior heat. That would make Ganymede's ocean more like a giant frozen battery than a living system. But here is where a new discovery gives us hope. Scientists have started to model something called radiolytic energy. It sounds complicated, but the idea is actually pretty simple. Jupiter is a beast. It blasts Ganymede with constant, brutal radiation. That radiation hits the surface ice and splits water molecules apart. It creates oxidants, things like hydrogen peroxide and oxygen. These chemicals are powerful. They are basically the same stuff we use to sterilize medical equipment on Earth, because it destroys organic matter. But in the context of an alien ocean, they become fuel. Here is the kicker. Those oxidants don't just sit on the surface. Over millions of years, they migrate. They work their way down through the ice, slowly drifting deeper and deeper, until they eventually reach the liquid ocean below. So you have this constant drip of highly reactive chemicals falling from the ice ceiling into the water. And on top of that, you have the opposite happening too. Radiolysis also produces hydrogen, and that hydrogen can diffuse upward from the ocean into the ice. So you get a chemical gradient. Oxidants coming down, hydrogen coming up. And where you have gradients like that, you have energy. You have the potential for life to grab that energy and use it. This is not science fiction. This is a working model being tested by astrobiologists right now. It suggests that Ganymede's ocean could be habitable even without hydrothermal vents. The radiation from Jupiter, the very thing that makes the surface of Ganymede a death zone, might be the thing that feeds life in the deep. It is a wild, counterintuitive idea, but it also means that landing on Ganymede is more dangerous than we thought. Because if we send a probe down there, we are not just drilling into an ice shell, we are breaking into a chemical reactor that has been sealed for billions of years, and we have absolutely no idea what is waiting on the other side. Let's talk about time. Not the kind we measure with clocks or calendars, but the kind that reshapes worlds. The ocean beneath Ganymede's icy crust is not young. It is not a recent geological accident. This body of liquid water has been there for 4 billion years. That is not a typo. 4 billion years. That is almost the entire age of the solar system itself. And it changes everything about how we think about life out there. Here on Earth, life got started fast. Really fast. Once our planet cooled down enough for liquid water to pool on the surface, it took maybe only 700 million years for the first living things to appear. That is not a long time in cosmic terms. It is basically the blink of an eye. So if life arose that quickly here, under the punishing heat of a young sun and a molten surface, what might have happened on Ganymede? Its ocean formed early, very early, and if life took root there, even in some primitive, humble form, it would have had a massive head start, a 4 billion year head start. Think about what that means. 4 billion years is enough time for single-celled organisms to evolve into forests full of dinosaurs and eventually into you listening to this. That span of time here on Earth produced brains, civilization, rockets. But Ganymede is not Earth, and that is where the story gets weird. Because here is the problem. Evolution does not just happen automatically. It needs energy, it needs pressure, it needs a reason to change. On Earth we had sunlight, volcanoes, tides, asteroid impacts, oxygen crises. We had chaos, and chaos drives evolution. But Ganymede is a different beast. Its ocean sits under 150 kilometers of ice. No light penetrates that. None. The only energy comes from hydrothermal vents on the seafloor, potential tidal flexing, and the slow radioactive decay of elements in the core. It is a dark world, a cold one, and a very, very quiet one. So here is the counterpoint. If life emerged in that ocean 4 billion years ago, it might not have gone anywhere. Not because it is stupid, but because there is no reason to change. In a stable, energy-starved environment, evolution slows to a crawl. The pressure to adapt is almost zero. You do not need a brain if you have no predators. You do not need movement if food drifts past you. You do not need complexity if simplicity works just fine. We call this the stagnant evolution hypothesis, and it is terrifying. Imagine this. Down there in the darkness, there could be microbes that are almost identical to the very first life that ever appeared on that world. 4 billion years of stasis. No arms, no eyes, no intelligence. Just an endless, patient existence in the cold. They would be ancient beyond anything on Earth. Living fossils that make our own stromatolites look like spring chickens. But here is the other side. What if we are wrong? What if evolution found a way down there, even in the dark? What if it found a niche, a chemical reaction we have not thought of, a loop that builds complexity without sunlight? Then we are not just drilling into a frozen ocean, we are drilling into a world that has been evolving alone for 4 billion years, and we have no frame of reference for what that produces. None. So the question is not just if we can land there. The question is whether we are ready for what we might find. So here is the uncomfortable truth, the one that keeps NASA astrobiologists up at night. We look at Ganymede, we see this vast global ocean, and our brains immediately paint a picture of an underwater Eden. We imagine glowing jellyfish, maybe some kind of alien anglerfish, a whole ecosystem thriving under the ice. It is a seductive thought. It feels like a sequel to a nature documentary. But the reality, the cold, hard, likely reality, is far more unsettling. It may not be a garden at all. It may be a desert. A pitch-black, high-pressure, lonely desert. Think about what it takes to build a complex food web. On Earth, almost everything depends on the sun. Sunlight hits the surface. Phytoplankton photosynthesize. Tiny creatures eat them. Bigger creatures eat those creatures. A chain of life stretching from the light down to the abyss. But under 50 miles of solid ice on Ganymede, there is no sun. None. Zero. So the entire engine of the ecosystem has to run on something else. It has to run on chemistry. Specifically, it has to run on the interaction between the salty ocean water and the rocky seafloor below. That process, called serpentinization, releases hydrogen and methane, and some microbes have learned to eat that. They are called chemolithotrophs, and they are the only candidates for life in that ocean. So stop imagining a bustling city. Start imagining a few scattered, desperate individuals clinging to cracks in the rock. The available energy down there is not a feast. It is a starvation wage. Every single calorie of energy has to be fought for. Scraped from a chemical reaction that might only happen in localized hotspots. For a complex creature like a worm or a fish, the metabolic cost of moving through that crushing pressure to find your next meal would likely exceed the energy you got from eating it. It is a brutal equation. You spend more energy hunting than you gain from the kill. In biology, that is a death sentence. What you get instead is a world of extremophiles. Single-celled organisms living on the knife edge of survival. They exist barely. They reproduce slowly, maybe once every 1,000 years. They drift in the darkness, living on a thin chemical margin, a film of potential energy that is barely enough to keep the lights on. It is a nasty, brutish, and short life, and when these cells finally die, there is no scavenger to eat them. Their bodies simply sink into the abyss, returning their precious atoms to the deep. This is the subversion we have to face. We want to find a cousin. We want to find a second Genesis. But what we are most likely to find is a microbial ghost town. A few lonely pioneers, holding on by their fingernails, in an ocean that has been chemically empty for eons. We are not looking for a bustling port. We are looking for a single flickering candle in a very, very long night. And the terrifying part is, that single candle is still more profound than anything we have ever discovered. Think about that for a second. A single candle burning in the dark. But what if that candle wasn't lit alone? What if the flame itself travelled here, across the void, hitchhiking on a chunk of rock? That's the heart of the panspermia hypothesis, and it shatters everything we think we know about life in this solar system. We tend to assume that life is a one-off miracle, an independent event. Earth gets its own spark, Mars gets its own spark, maybe Europa or Ganymede gets its own. But what if it doesn't work that way? What if the universe is actually one big, messy, interconnected petri dish? Here's the thing. When a big enough asteroid smacks into a planet, it throws up debris. We're not talking about a few pebbles. We're talking about massive chunks of crust, blasted into space with enough force to escape the planet's gravity. And inside those chunks, protected from radiation, microbes can survive. For tens of thousands of years, they go dormant, they wait. And then, if that rock happens to fall into another world's ocean, they wake back up. We have proven this is possible. We've found Martian meteorites here on Earth. So pause and ask yourself a deeply uncomfortable question. If Ganymede has a liquid ocean, and if that ocean has been there for billions of years, could the life we find there actually be our own distant cousins? Could a single impact event, billions of years ago, have seeded both worlds? It flips the script. Suddenly we're not looking for a separate alien creation. We're looking for a lost colony, a fragment of our own family tree that got stranded in the deep. And that's the false limit. It's our stubborn assumption that life is a lonely island in each ocean. But the truth, the terrifying truth, might be that the entire solar system is one connected ecosystem, that every time an asteroid hits a world, spores are scattered like seeds on the wind. It means that if we find life on Ganymede, we might not be discovering something new. We might be rediscovering something we lost a long, long time ago. That candle in the dark. It might have been lit by the same fire that lit our own world. And that connection, that cosmic kinship, is far more profound than finding something completely alien. It means we are not alone, but we have never been separated either. And here is where the frustration really sets in. You'd think that with all our technology, with all the money and brainpower we've thrown at space, we'd have a way to check, to just peek under the ice and see if there's something swimming around down there. But we can't. And I mean that literally. We have no tool, no instrument, no trick in the book that can tell us if there's a single living microbe in that entire ocean without actually going there and drilling through. It's a maddening silence. SETI has pointed its telescopes at Ganymede. They've listened for radio signals, for any kind of deliberate transmission, for the kind of chatter you'd expect from an intelligent civilization. And they got nothing. But that's not surprising. In fact, it's almost beside the point. Because the life we're talking about here isn't building antennas or sending out greetings. It's microbial, bacteria, single-celled things that don't care about radio waves. They don't broadcast. They don't announce their presence. They just exist silently in the dark. So here's the real problem. There is no remote detection method for non-technological life. None. Zero. You can't look at Ganymede through a telescope and see the chemical signature of living organisms because the atmosphere is practically non-existent. It's a vacuum. There's nothing to analyse. On Mars we can sniff the air for methane, which might be produced by life. But Ganymede doesn't have that luxury. No atmosphere means no biosignatures in the air. The ocean is sealed under 150 kilometres of ice, and that ice blocks everything. Light, radiation, any signal a living thing might accidentally produce. It's like trying to read a book locked inside a concrete safe. And you don't have the key, which leads to the cruelest irony. The best candidate for life in the solar system is also the one where we are most completely blind. Think about that for a second. We have this enormous, seemingly perfect ocean, liquid water, tidal heating, the right chemistry. Everything we know about life says it should be there, and yet we cannot prove it. We cannot see it. We cannot hear it. The ocean is there, sure, but what's in it? That's the question that haunts every planetary scientist. Because until we send a lander, until we drill through that ice and drop a probe into the water, we're just guessing. And guessing never got us anywhere. It's a silence problem, a true limit. And it's one of those rare moments where science has to admit it's powerless. We can't check the box. We can't confirm or deny. All we can do is stare at that moon and wonder. And that wonder, it's a lot more terrifying than you might think. Because if we're wrong, if there's nothing down there, then that candle in the dark we talked about, it might be the only one. And that brings us to a terrifying idea that some scientists are actually starting to take seriously. It is called the icy prison hypothesis. And it might just be the most depressing explanation for the Fermi Paradox we have ever come up with. You know the Fermi Paradox, right? The universe is vast, ancient, and filled with the raw ingredients for life. The numbers are staggering. There should be countless civilizations out there. But we look up at the night sky, and it is utterly silent. No radio signals, no alien artifacts, no cosmic chatter, just the cold, empty hum of the stars. We have always assumed that if life exists, it will eventually become intelligent and ambitious. It will build spaceships, send out signals, colonize its solar system. But what if that assumption is dead wrong? What if the problem is not that life is rare, but that life is stuck? Think about what Ganymede is telling us. It has a massive ocean of liquid water, more water than all of Earth's oceans combined, buried under hundreds of kilometers of ice. And we have already established that this ocean is probably stable, warm, and chemically rich. It should be the perfect place for life to emerge. And if it does, that life will likely be simple, microbial, swimming around in a completely dark, pressurized world. And it will never know the stars exist. It will never see the sun. It will never build a radio telescope, because it doesn't even know there is a sky to look at. That moon is a cage. A perfect, life-giving cage. And the terrifying part is, Ganymede is not the exception. It is the rule. Look at the moons of Saturn. Enceladus has it. Europa almost certainly has it. There are even hints that Pluto might harbour a liquid ocean under its frozen shell. The universe might be absolutely teeming with life, locked away in these watery prisons, eternally trapped beneath miles of solid ice. Here on Earth, we got lucky. We got to break out. Our planet's oceans is on the surface, warmed by a nearby sun. We had a chance to crawl out of the water, grow lungs, look at the sky, and eventually build rockets. But that seems to be the rare exception. The statistical outlier. The one fish that grew legs and crawled onto land, while every other fish in every other ocean stayed blissfully unaware of the universe outside their world. Imagine standing on the edge of an ocean, looking up and seeing nothing but a ceiling of ice. No moon, no stars, no light, just the crushing weight of an entire world pressing down on you. You have no idea that there is anything else. You don't know about other worlds, other suns, other lives. You just swim forever. And that might be the normal state of life in the cosmos. So ask yourself this. We look at Ganymede and see a potential cradle for life. But what if we are looking at the reason the universe is silent? What if every ice-covered moon out there is a jail cell, and every potential civilization is serving a life sentence, stuck in the dark, forever cut off from the stars? We might have finally found the answer to that haunting question. Where is everybody? They are right here. They are everywhere. They are just trapped. And that candle in the dark we talked about, the one we lit with our first radio signal and our first rocket, might be the only flame in an ocean of ice, the only one that ever got out. Decades of work, a few seconds of data. That is the story of our attempt to understand Ganymede. We have identified this hidden ocean world, but getting there has been a long, frustrating, and humbling voyage. We haven't just been knocking on Ganymede's door for a few years. We have been sending postcards, shouting into the void, and hoping someone picks up for almost 50 years. The first real look came in the 70s, when Pioneer and Voyager screamed past the Jupiter system. They were in a hurry, flying by at tens of thousands of miles per hour. We didn't land. We didn't study. We got a handful of grainy images, a few minutes of data, and then those ships were gone, hurtling out into the black. It was a tease. We saw this massive, pockmarked world, bigger than Mercury, with cracks etched by some cosmic hand. And we wondered if something was moving down there under that thick crust. Then came Galileo. That mission stuck around for 8 years. From 1995 to 2003, circling Jupiter and getting a much closer look, Galileo found the magnetic field, the first real smoking gun. It sensed something strange beneath the surface, something that could conduct electricity. But even Galileo could not confirm the ocean. It could only point and whisper. So here we are with all this history and yearning, and we have never touched the surface. All that effort, billions of dollars and thousands of brilliant minds, and we have only ever seen Ganymede from a distance. It is like staring at a beautiful frozen lake from a helicopter, knowing there is a world swimming beneath the ice, but having no way to break through. We are desperate to get closer, but the journey is only getting harder. And so it was, in the cold, dark spring of 1979, that we got that first blurry, unforgettable glimpse. Voyager 1 and then Voyager 2, those twin robotic explorers we sent out into the void, swept past Ganymede like a couple of cosmic tourists with a single-use camera. But what they saw blew the doors off everything we thought we knew. Before Voyager, Ganymede was just another rock, a pale dot in the eyepiece of history. After Voyager, it was a world. Those grainy images beamed back across 500 million miles of nothing showed something we had never seen on a moon. A twisted, chaotic surface covered in grooves. The scientists back on Earth called it grooved terrain. Picture it yourself. Like someone took a giant ice cube and scraped a fork across it in long, parallel lines, then smudged it all together. It was a landscape of ridges and troughs that hinted at immense geological forces, forces that should not exist on a frozen moon so far from the sun. And then came the real kicker. In the same flyby data, instruments picked up signs of something incredibly thin, an atmosphere. Not the thick, breathable air we have here, but a ghost of an atmosphere, a wisp of oxygen so tenuous it barely qualifies as a presence. Can you imagine? A moon of Jupiter, deep in the radiation belts of the solar system's biggest bully, wearing a coat of oxygen. It was our first clue that Ganymede was not dead. It was not silent. It was doing something. That first glimpse was just an overture. The real symphony, the deep dive, would have to wait for the next generation, and that generation arrived in the form of Galileo. Now Galileo was a veteran. It launched in the belly of the space shuttle Atlantis back in 1989, and by the time it entered orbit around Jupiter in December of 1995, it had been travelling for 6 long years. It was a cranky old spacecraft too, with a stuck high-gain antenna that forced the team on the ground to get creative with data compression. But boy, did that stubborn machine deliver. Over the next 8 years, Galileo conducted 6 dedicated flybys of Ganymede. 6 times it swung past that icy sphere, getting closer and closer, until it was skimming just a couple 100 miles above the surface. And what it found on those flybys changed everything we thought we knew about moons and oceans, and where life might possibly exist. The biggest bombshell dropped in 1996. As Galileo swooped past Ganymede for the second time, its magnetometer, that little instrument designed to sniff out magnetic fields, suddenly went haywire. Ganymede had its own magnetic field, not a residual one, not a weak one, a strong dipolar magnetic field, the kind you only see on planets like Earth. Ganymede was the only moon in the entire solar system with this feature. It was a moon acting like a planet, and that magnetic field was the smoking gun for something even more mind-boggling. You see, a magnetic field that's strong requires a liquid conductor moving around inside. On Earth, it is molten iron. On Ganymede, it had to be salt water. The magnetometer data was the first indirect but incredibly powerful piece of evidence for a liquid ocean beneath the crust. It was not just a hunch. It was physics. The field was fluctuating in a way that only an electrically conductive ocean, sloshing around under the influence of Jupiter's immense magnetic field, could explain. This was the process of electromagnetic induction. It was like listening to the ocean whisper to us through a radio signal, a signal that said, "I am here, I am liquid, and I am deep." But Galileo was not done. On its final flyby in 2003, the mission controllers faced a terrible choice. The spacecraft was running out of fuel, and its orbit was decaying. They could not risk an out-of-control crash into Europa or Ganymede, those pristine, potentially habitable worlds. The fear of contamination was too real. If there was life in that hidden ocean, we could not risk sprinkling earthly bacteria from a dead spacecraft all over it. So they made the call. They sent Galileo on a kamikaze dive into Jupiter's crushing atmosphere. It was an intentional suicide. The spacecraft burned up, vaporized into a streak of atoms, rather than risk tainting the very ocean it had discovered. That is the sacrifice of science. That is how much we fear what we might accidentally do. We know the ocean is there, we know it is real, but we have only ever touched it with echoes, with magnetic whispers, and with the ghost of a burned spacecraft. And now we are terrified to go back. In the beginning, that ocean beneath Ganymede's frozen shell was just a ghost, a mathematical whisper from the Galileo probe. It was a tantalizing guess, a chess move built on gravity and magnetism, but it wasn't proof. Not really. The real turning point came in 2015, when a team of astronomers did something incredibly clever. They used the Hubble Space Telescope to look at Ganymede for 20 hours straight. That's an agonizingly long time for Hubble, a telescope that has to beg for every second of its schedule. But this was worth it. They weren't looking for ripples on an ocean you cannot see. They were looking for the ocean's fingerprint. You see, Ganymede has auroras, just like Earth. But here's the trick. Those auroras don't dance the way they should. They wobble. And the reason they wobble is the ocean. As the subsurface saltwater sloshes around, it creates a tiny magnetic field of its own, a secondary push that fights against Jupiter's massive grip. This magnetic tug-of-war makes the aurora rock gently back and forth, and by measuring exactly how much it rocks, Hubble gave us our most undeniable proof yet. It was the scientific equivalent of shining a flashlight under a locked door to see if someone is inside. We saw the shadow of the ocean. That 20-hour campaign changed everything. It took the ocean from a strong suspicion to a published, peer-reviewed fact, and it opened up a new era of curiosity, because for all Hubble's genius, it could only give us a blurry, two-dimensional sketch of that auroral wiggle. The James Webb Space Telescope, on the other hand, can see in the infrared. It can smell the chemistry of that thin, tenuous atmosphere. It can look for plumes of water vapour, spitting out from cracks in the ice, plumes that Hubble might have missed. Webb could give us the composition of that ocean without ever touching the surface. But even Webb has its limits. It can map the surface, it can taste the exosphere, but it cannot look through 1,000 kilometres of ice to see if something is swimming there. We are still, in essence, blind. We are sitting on the shore of an alien world, knowing a vast, dark sea is right there, and we are too terrified to build a boat that might not survive the landing. 4.4 New Discovery, JUICE, the European pioneer. So here we are, sitting on the shore like I said, staring at an ocean we cannot see, cannot touch, cannot even really prove exists in any meaningful detail. And yeah, it's a little terrifying. But you don't solve a mystery by staring at it. You solve it by building the best damn boat you can, even if you're scared it might sink. That's exactly what the European Space Agency did. They built a boat, well, technically a spacecraft, and they called it JUICE, Jupiter Icy Moons Explorer. It launched in April of 2023, riding an Ariane 5 rocket up from French Guiana. And if everything goes right, if the gravity assists line up, if the radiation belts don't fry its brains, it will arrive at Jupiter in July of 2031. That's a long flight. 8 years. But space is big and patience is cheap. Now JUICE is not a lander. Let's be clear about that. It's not going to sit on the ice and cough up a drill. It's going to fly. Specifically, it's going to perform 35 flybys of Ganymede. 35 close, screaming passes, each one burning past the moon at a few kilometres per second, grabbing data before the gravity of Jupiter yanks it away again. Then, in December of 2034, after those flybys have mapped the beast from every angle, JUICE does something incredible. It slows down. It fires its engines and slips into orbit around Ganymede itself. That's the first time any human spacecraft will orbit a moon other than our own. Think about that. We've orbited the moon, we've orbited Mars, we've orbited Saturn, but we've never just parked around a moon of a gas giant. Ganymede gets that honour. Why does this matter? Because JUICE is carrying the tools we need to finally answer the big questions. The centerpiece, the real monster on board, is a radar antenna. It's 10.4 meters across. That's bigger than a city bus. It's designed to fire radio waves down through the ice and listen for the echoes bouncing back from the liquid water below. This thing can penetrate 9 kilometers deep. 9 kilometers. That's deeper than the entire crust of Ganymede, which is probably only about 150 kilometers thick in the first place. But here's the thing, the ice might be dirty. It might be cracked. It might be full of salt or ammonia. The radar wave might scatter. It might get confused. But if there is a global ocean down there, if the ice is even a little bit transparent, JUICE will see it. It will map the depth, the boundaries, maybe even the internal currents. It will give us the first real direct evidence that the ocean is real, not just a mathematical guess. Then there's the magnetometer. It's a simple instrument. It measures magnetic fields. But on Ganymede, that's a cheat code. Ganymede is the only moon in the solar system with its own magnetic field. It generates it, somehow, probably because of the liquid, conductive ocean sloshing around in its mantle. By mapping how that magnetic field wobbles and changes as Ganymede orbits Jupiter, JUICE can infer the electrical conductivity of the interior. And electrical conductivity tells you what the water is made of. Salty water conducts differently than pure water. Different salts produce different signals. We might be able to figure out if the ocean is briny enough to support chemistry, maybe even life. And you cannot forget the ultraviolet spectrograph. It sounds boring, but it's not. It looks at the surface in ultraviolet light, and the way sunlight reflects off the ice tells you exactly what molecules are sitting there. Salts, organic compounds, maybe even complex carbon chains. If Ganymede's surface has been contaminated by material welling up from below, we will see the chemical fingerprints. We will know what's drifting on the currents down there, at least indirectly. JUICE is not a pioneer. That's the wrong word. It is a surveyor, a cartographer. It is the one who draws the map before you send in the soldiers. And that map is absolutely critical because the fear, the terror, the reason NASA is so hesitant to land, it all comes down to one thing. We don't know what the ground feels like. We don't know if it's hard as concrete or soft as powder. We don't know if it's covered in dust or wrinkled with crevasses. JUICE will tell us. It will photograph the landing sites. It will measure the ice density. It will watch for plumes, for vents, for anything that might punch a hole in a landing craft. And by the time 34 rolls around, when JUICE finally enters orbit, we will have a map. A real map, not a guess, not an estimate, a blueprint for the next step. But here is the uncomfortable truth. Even with that map, the fear does not go away. It just changes shape. Now we know exactly where the danger is, and we have to decide if we are brave enough to go anyway. This brings us to the most fascinating, and possibly the most frustrating part of this story. We aren't going in blind. We have a scout. Her name is Europa Clipper, and she is already on her way. A tiny spacecraft hurtling through the void, heading for a world that might hold the very secret to life itself. Europa Clipper arrived in the Jovian system back in 2024, and by the year 2030, she will be settled into orbit, ready to work. You might think naming her after Europa instead of Ganymede is a bit rude, a bit of sibling rivalry. But here is the thing. These two moons are not rivals. They are partners. They are the only two worlds in the entire solar system that we know of that have a global subsurface ocean of liquid water locked away beneath a shell of ice. So, what happens when Europa Clipper starts flying past her namesake? She is going to do something incredible. She will fly by Europa 49 times, coming as close as 25 kilometers to the surface. That is a terrifyingly low altitude. From that vantage point, she will map the ice, analyze its composition, and sniff the thin atmosphere for any sign of a plume. A geyser of water erupting from the southern pole, spewing the contents of the ocean into space for us to taste from a distance. Imagine Clipper finding active plumes on Europa. It would be the single greatest discovery in planetary science since the Voyager missions. It would change everything. Suddenly, we would have a target, A place where we can grab a sample of an alien ocean without landing, without drilling, without risking our precious rover getting crushed by a mile of shifting ice. And that is the connection to Ganymede. Everything Clipper learns about Europa will be a cheat sheet for the Jupiter Icy Moons Explorer, the European JUICE mission, which is also on its way, a little slower, a little more deliberate. JUICE is going to Ganymede. It arrives in December of 2034. So right now we are in a golden age of Jovian exploration. We have 2 incredible spacecraft, 2 robotic ambassadors, heading for the most promising real estate in the cosmos. Clipper will tell us how active these icy shells are. It will tell us if the ice cracks, if the ocean vents, if the radiation is survivable. It will provide the comparative data we desperately need. Because here is the uncomfortable truth that shifts the fear. If Europa Clipper finds the surface of Europa is geologically dead, the ice too thick, the plumes just a fantasy, then our hope rests entirely on Ganymede. All bets are off. The fear we have for landing on Ganymede becomes a terrified hope. It means Ganymede is the only game in town, and we have to get it right. Clipper is not just a companion. She is the scout who tells us if we are charging into a battlefield or walking into a garden. And that brings us to the next chapter. The JUICE mission, the Jupiter Icy Moons Explorer from ESA, is not just a fancy flyby. It is the single most important piece of exploration hardware we have ever sent to this frozen world, and it is about to answer the questions that keep planetary scientists up at night. So what exactly is JUICE going to tell us? Let's be real for a second. We have guesses about Ganymede. We have educated guesses based on Galileo data from the 90s, but that data is grainy and old. It is like trying to read a newspaper through a foggy window. JUICE is going to clean that window. First, it will refine the ice shell thickness. And I do not mean a rough estimate. I mean down to the kilometre. We will know exactly how much frozen water sits between us and the ocean below. Is it 10 kilometres thick? Is it 100? That number changes everything for a lander. If the ice is thin, the crust is unstable. If it is thick, we have a stable platform but a much deeper drilling problem. JUICE will tell us where the sweet spot is. Second, and this is the big one, it will confirm the presence of a rocky seafloor or a high-pressure ice floor. You see, there is a chance that the ocean of Ganymede is not sitting on rock like Earth's oceans. It might be squeezed between layers of exotic ice so compressed by the planet's gravity that it behaves like a solid, dense mineral. If the ocean floor is rock, we have hydrothermal vents. We have chemistry. We have a plausible environment for life. If it is high-pressure ice, the ocean is a dead end. A sterile, cold, dark bathtub. JUICE will use its magnetometer and gravity mapping to feel the bottom of that ocean without ever touching the water. It will listen to Ganymede's heartbeat. And finally, it will map over 80% of the surface at 400-meter resolution. That is not satellite imagery. That is reconnaissance photography. At that resolution, we will see individual impact craters in detail. We will map the tectonic fractures. We will spot the landing sites that are safe, and more importantly, the ones that are deadly. This survey will be the blueprint. Every future mission, every lander that we ever send, will have its design based on these maps. Engineers back on Earth will look at JUICE data and decide exactly how thick the landing legs need to be, how much radiation shielding is required, and whether we even dare to drill. So put yourself in the shoes of the mission planners. JUICE is not just a science spacecraft. It is the scout that draws the map for the invasion. Without this data, a Ganymede lander is a gamble. With it, it becomes a calculated, informed, terrifying leap into the unknown. And that is exactly the kind of leap we are about to take. The terror of Episode 2 isn't just academic fear. It's terror solidified into policy. When you look at the roadmap for the next decade of planetary science, you see something strange, something almost insulting, if you're a fan of Ganymede. We call it the Decadal Survey. Every 10 years, the smartest minds in the solar system gather, argue, and decide what flagship missions are worth the money. It's a brutal, competitive process. When the last survey came out, Europa got a seat at the big table. Europa got a dedicated lander study. But Ganymede? Ganymede got flybys. That's the polite word for a brush-off. Think about the sheer insanity. The largest moon in the solar system, the only one with its own magnetic field. An ocean that might hold twice the volume of all of Earth's salt water combined. And we're sending it tourists with window seats. We're not landing. We're waving as we drive by. The reason for this empty slot isn't bad science, it's bad timing and ugly math. The political and budgetary reality is a monster hiding under the bed. A Europa lander is sexy. It's the poster child for life hunting. It sells subscriptions and congressional votes. Ganymede, on the other hand, is the quiet genius. Less flashy, deeper, harder to reach. To park a lander there, you have to fight Jupiter's radiation belts for days, then survive on a surface that is a frozen desert with ice so weird it behaves like rock. That kind of engineering costs political capital we haven't saved up yet. Here is the uncomfortable truth you need to sit with. Every lander needs a champion. Not a scientist, but a generational champion. A politician or administrator who bleeds for the mission and shoves it through budget justifications for years. Cassini had a generation of champions. Apollo had warriors willing to burn their careers. For Ganymede, those champions have not risen, or they haven't been given the ammunition they need. That is where the terror lives. The terror isn't that we can't land there. It's that we might never try, because the waiting list for a flagship mission is longer than our careers. To build a Ganymede lander, you're looking at a 20-year pipeline from concept to touchdown. 20 years of keeping the flame alive through 5 presidencies. 20 years of justifying the cost while other moons scream louder for attention, and so the empty slot remains. A ghost on the roadmap, a massive hole in our manifest. We know the ocean is there, we can see the salt, we can smell the possibility. But the reality is brutal. Europa has the lander study because the community screamed louder. Ganymede is left with flybys because the community is still gathering evidence, still building the case. JUICE is that evidence. It's the dossier we will hand to the next generation of champions, hoping they have the nerve to pull the trigger. Because if we don't find a champion soon, the slot stays empty. That hidden ocean remains hidden, not just by ice, but by paperwork. And that is the scariest thing in this entire story. The universe is willing to share its secrets, but only if we are willing to wait for the right generation to ask the question. But here is where the story takes a sharp, unexpected turn. A turn that terrifies NASA, not because of radiation or ice, but because of a flag. For decades, the exploration of Ganymede has been stuck in a slow, bureaucratic crawl. We have the tech, we have the will, but we do not have the political push. Think about that for a second. The single greatest ocean in the solar system, right under our noses, and we are hesitating because of a budget line item. That is the impasse, and it is an impasse that might finally be broken by a rival. Let me introduce you to the wildcard, China. You have heard of Tianwen-1, the mission that put a rover on Mars. But Tianwen-4 is a different beast entirely. This is not just a flyby, this is a lander. A Chinese lander, aimed directly at the heart of Jupiter's biggest moon. And here is the kicker. They are not messing around. They have the rockets. They have the nuclear power sources. And most importantly, they have the patience. The Chinese space program plays the long game. They are not pressured by quarterly reports or congressional hearings. They set a target, and they move toward it with a single-minded focus that the West has frankly forgotten how to match. This is where the historical parallel kicks in. Remember the old space race between the US and the Soviet Union. It was messy, it was competitive, but it got things done. We walked on the moon not because it was easy, but because the Soviets were breathing down our necks. That rivalry was a catalyst. It turned dreams into deadlines, and now we are seeing the same dynamic play out around Ganymede. China wants the prestige. They want to be the first nation to touch that alien ocean. And that desire for glory, that national pride, is exactly the fuel that the US space program has been missing. So here is the uncomfortable truth. NASA might be terrified of the risks, all that radiation and the political fallout of a failed mission. But they are even more terrified of coming in second place. The fear of losing face might just override the fear of losing a probe. If China plants a flag on that ice shell, the entire geopolitical calculus shifts. Suddenly, the paperwork is no longer an excuse. The funding magically appears. The silence from NASA breaks. And that hidden ocean, once locked behind a wall of caution, becomes a racetrack. The question is, will we be watching from the stands, or will we be running the race? The 10-year journey. That is the cold, hard arithmetic of exploring Ganymede. You do not just build a spacecraft, strap on extra fuel and point it toward Jupiter. The launch window is a cruel sliver of celestial geometry, opening once every 13 months. Miss it, and you wait another year. Once the probe is finally off the ground, it takes 7 to 8 years just to get there, drifting through the void on a patient, looping trajectory. That is a decade of your life, from launch to orbit, and that is before the lander even separates. Then add the planning, the engineering, the testing. Every bolt on a lander destined for Ganymede must survive a decade of deep space radiation, then slam into an icy crust that could be soft snow or solid rock. You cannot rush that. A mission like this eats a generation of careers. Scientists spend their entire professional lives designing instruments that will never return a single data point until they are already retired. That is the true limit, not technology, not politics, but time itself. So, what does that timeline look like? Realistically, with current budgets and priorities, a Ganymede lander is a creature of the 2050s. That is the earliest we can dream of touching that hidden ocean. 3 decades from today. 3 decades of funding cycles, shifting political winds, new presidents, new space agencies and new crises that will try to steal that budget for 100 other causes. It is a marathon of patience, a test of whether our species can commit to a goal beyond our own immediate horizon. The terrifying part is not the ice or the radiation. It is the nagging question of whether we will still have the will to finish the race when the starting gun fired before half of us were even born. And so, as we look up at that tiny dot of light in the Jovian sky, we have to ask ourselves, what are we really doing here? The JUICE mission is already in transit, a silent hitchhiker riding the gravity of planets, carrying the hopes and sweat of scientists who first sketched this journey on napkins decades ago. They were young then, full of fire and certainty. Some have retired. Some have passed away, but the spacecraft keeps going. It is a generation ship, not of colonists, but of pure data. We are sending a message in a bottle, launched from a shore we might not be standing on when it finally washes up. It will take years to arrive. Years to decode, years to understand, and that is the quiet terror of exploration, isn't it? The race doesn't end when you cross the finish line. It ends when your grandchildren get to read the results. So the question for us is simple. Will we have the patience to wait for the bottle to reach the other side of the ocean, or will we turn away before the answer even has a chance to knock on our door, knowing everything we know about the terror of getting there, the planet it's hiding, and the missions on the way? What happens next? How do we break in? That's the question that keeps scientists up at night, staring at the ceiling, imagining a world buried under 100 miles of ice. We've sent orbiters, mapped its surface, even caught glimpses of its salty ocean from afar. But cracking that shell, actually touching the water below, feels like trying to open a safe with a butter knife. Here's the thing about the next century of exploration. It's not about being fast. It's about being patient. NASA's got the Europa Clipper on the way, and JUICE from the European Space Agency is already zipping through the solar system. But those are just scouts. They'll fly by, take pictures, sniff the atmosphere, and tell us if there's any hope. The real mission, the one that lands, drills and peers into the abyss, is still a blueprint on a whiteboard somewhere. Think about it. We're talking about a robot that has to survive radiation that would fry a human in minutes, land on a surface colder than Antarctica, and then melt through miles of ice without breaking a single seal. That's not a 5-year project. That's a 50-year project. The terrifying part is the people who start it might never see it finish. But that's the deal. We're not just sending machines. We're sending our curiosity, wrapped in titanium, hoping it reaches a place we'll never go. So how do we break in? We don't rush, we prepare, we build. And then one day, we lower the first probe into a darkness that hasn't seen light for 4 billion years. And that brings us to the next chapter of this story. Wanting to explore the hidden ocean of Ganymede is one thing. Actually doing it, that's a whole other beast. We have to ask ourselves a hard question. Do we even have the tools yet? The honest answer is no. Not really. We have blueprints and concepts, but the technology needed to survive on Ganymede and pierce its icy shell is still sitting in labs and computer simulations, waiting for breakthroughs that might take another decade or two. Let's start with the journey itself. Jupiter is, on average, about 484 million miles from Earth. Even with current chemical rockets, a trip to Ganymede takes around 6 years. That's a long time to keep a spacecraft alive, let alone a crew if we ever get that far. So what do we need? Nuclear thermal propulsion. This isn't science fiction. We tested similar ideas back in the 1960s. But scaling it up, making it reliable, and proving it can cut travel time in half or more. That's the million-dollar question. A nuclear thermal rocket uses a reactor to heat propellant directly, providing far more thrust per pound of fuel than anything chemical. But the safety concerns are enormous. You're essentially carrying a small nuclear reactor into space. One malfunction, one launch failure, and you've scattered radioactive debris across the coast of Florida. So we're making progress, but it's slow and cautious. Nobody wants to rush that. Once you arrive at Ganymede, you need power. And we're not talking about a few solar panels. Sunlight there is about 25 times weaker than on Earth, making solar power essentially useless. So you need a compact fission reactor. NASA has a program called Kilopower, which is exactly what it sounds like. A small, reliable reactor designed to produce between 1 and 10 kilowatts of electricity. That's enough to power a small habitat, run scientific instruments, and keep electronics from freezing in the brutal cold. But here's the catch. These reactors are still in testing. They've run them on the ground, but nobody has flown one to deep space and proved it can operate flawlessly for years without maintenance. Radiation from the reactor itself also complicates things. You have to shield everything, which adds weight, and weight is always the enemy. Then there's the elephant in the room, Jupiter's radiation belt. It is absolutely merciless. Any electronics sent to the surface or into the subsurface ocean must be hardened against radiation levels that would fry a standard computer chip in hours. We're talking about materials that can withstand the equivalent of 1 million chest X-rays. That requires specialized semiconductors like silicon carbide or gallium nitride, which are still expensive and difficult to produce. We're making headway, but it's not a solved problem. And what about actual exploration once you're there? You can't just drill through Ganymede's ice sheet with a remote control. The signal delay from Earth to Jupiter ranges from 30 to 50 minutes, depending on orbital positions. So you need autonomous AI. The probe has to think for itself, making real-time decisions about where to drill, how to navigate cracks in the ice, and how to avoid getting stuck. We're getting better at AI, but trusting a machine to make life or death decisions for a mission costing billions of dollars, that takes a whole new level of confidence. Finally, you have to live off the land. In situ resource utilization, or ISRU. That means melting ice for water, splitting it into oxygen for breathing, and hydrogen for fuel, maybe even mining the surface for materials to build replacement parts. We're testing these ideas on the Moon and Mars now, but Ganymede is an entirely different environment. The cold, the radiation, the low gravity. Every system has to be rethought, re-engineered, and proven on Earth first. So where does that leave us? Nowhere near ready, but closer than we were a decade ago. Every breakthrough in nuclear propulsion, radiation-hardened electronics, and autonomous navigation brings that moment a little closer. The day we finally lower that first probe into Ganymede's hidden ocean won't be luck. It will be the result of engineers and scientists solving problems we haven't even fully defined yet. And that's the real work. That's the grind. The ultimate question, then, is how we crack that shell. Not with a drill, not with a hammer, but with something far more elegant. something that sounds like science fiction but is already being built in a lab. We call it a cryobot. The name gives away the trick, cryo as in ice, bot as in robot. It's a robotic probe designed to melt its way down through miles of frozen water. It's not a new idea. People have been kicking it around for decades. But the engineering, the sheer physics of pulling it off, that's a nightmare we are just beginning to wake up to. So picture this. You drop a cryobot onto the surface of Ganymede. It lands, settles into the ice, and then it starts to heat up. The nose of the probe, or its belly, depending on the design, becomes a giant hot plate. The ice directly beneath it melts into a thin film of water. Gravity pulls the probe down, or if you're clever, the water refreezes above it and pulls it down like a pipe. It's a descent powered by controlled constant melting. The probe leaves a smooth, narrow shaft of liquid water in its wake, which almost instantly freezes back into solid ice behind it. It's a one-way trip. You are effectively sealing yourself into the ice as you go, and you have to carry all the heat you need for the entire journey. That means a nuclear power source, probably a small radioisotope thermoelectric generator or some kind of mini-nuclear reactor. It's not exactly a battery you can swap out. Now, we aren't just guessing this will work. We've been testing it. NASA has a project called Valkyrie, which stands for Very Deep Autonomous Laser-Powered Kilowatt-Class Yo-Yoing Robotic Ice Explorer. That's a mouthful. But what it actually is a cryobot that uses a high-powered laser beamed from the surface to melt its way down. They tested it in the frozen hellscapes of Antarctica, in the Matanuska Glacier in Alaska, in the ice tunnels of Greenland, and it works. On Earth we can melt through 100 meters of ice, maybe even 1,000. But Earth ice is a cakewalk compared to Ganymede, because Ganymede's ice shell isn't just cold, it's deep. It's 300 kilometers deep, and that's where the plan hits a wall. The problem is high-pressure ice. You see, ice isn't just one thing. When the pressure gets high enough, the molecular structure of water changes. You get different phases. You've got your standard everyday ice, what we call Ice 1. But down on Ganymede, as you descend past roughly the first 150 kilometers, the pressure becomes so immense that the ice transitions into a new phase called Ice 3. It's denser, colder, and more stable. And if you keep going, you hit Ice 5, and then eventually, near the ocean floor of the ice itself, you hit Ice 6. These high-pressure ices are monsters. They don't melt the way normal ice does. They have much higher melting points. You can't just pump heat into them and watch them turn to water. They require far more energy to break their molecular bonds. The standard cryobot, even one powered by a nuclear reactor and a laser, would run out of juice before it even got halfway to the ocean. The ice becomes a thermal barrier that is, for all practical purposes, impenetrable. This is the mission killer. You can design the most beautiful, elegant, autonomous melting probe in the solar system. You can test it on every glacier in our backyard, but when you drop it into the Ganymedean ice, you hit that high-pressure wall and your probe becomes nothing more than a frozen artifact, a shiny memorial to a good idea. It gets stuck. It's trapped. The heat it generates is no longer enough to overcome the structural integrity of that deep ice. The probe's electronics fail, the power source decays, and it just sits there, a tiny warm spot in a frozen hell for the next billion years. And this is why, right now, many scientists are quietly turning their attention to Europa. Europa's ice shell is much thinner. We are talking about 15 to 25 kilometers, not 300. And it's mostly standard, low-pressure ice. A cryobot could theoretically punch through Europa's crust in a matter of days, or weeks, not centuries. But Ganymede has the bigger ocean. It has the deeper, more stable water column. It's scientifically the richer target. Yet, the sheer physics of getting down there looks like a wall we can't climb. Not with current technology. Not with any technology we can realistically project for the next 50 years. It's a sobering thought. We have the destination. We have the motivation. We have a solid theory of what lies beneath. But the journey itself, the act of descending through 300 kilometers of murderous, high-pressure ice, may require a breakthrough we haven't even imagined yet. Maybe it's a swarm of tiny melting bots that work together. Maybe it's an entirely new form of drilling that uses sound or shock waves to destabilize the ice. Or maybe, just maybe, we have to accept that Ganymede's secrets are locked away for the next century, waiting for a generation of engineers who can solve a puzzle we can barely comprehend. And that's the grind. That's the real frontier. Not just building the probe, but rethinking what a probe even is. But here's where the story stops being about fear and starts being about ambition. Because if we can't land on Ganymede's surface, maybe we shouldn't even try. Instead, picture this. It's the 22nd century, and humanity has built something that sounds like pure science fiction, but is actually just stubborn engineering. A permanent base on Ganymede. Not on the surface, because that ice crust is still a nightmare. No, we burrow. We carve a habitat 100 meters beneath that frozen shell, where the pressure stabilizes and the radiation from Jupiter's hellish belts can't touch us. The ice above becomes our shield, tons of frozen water absorbing everything the giant planet throws at us. And that magnetosphere? The one that terrifies NASA right now? For a settled colony, it's a gift. It deflects the worst of the solar wind, giving our subsurface home a layer of protection that Mars colonists would kill for. We'd use that water for everything. Melt it, filter it, drink it. Split it into hydrogen and oxygen for rocket fuel. No supply ships needed from Earth every 6 months. Ganymede becomes a gas station for the outer solar system. And here's where it gets really wild. Remember the old science fiction, from writers like Robert Heinlein, who wrote about the Moon being a penal colony and Mars a frontier town. This is that same spirit, but grounded in 22nd century realism. We're not flying to Ganymede because it's easy. We're flying there because it has everything we need to stay. Water, energy, a natural radiation shelter, and a gravity field that won't wreck your bones as badly as living on a space station. Imagine a base built from modular habitats, lowered through a borehole, each module connecting like a stack of cans. The ambient temperature outside is a balmy negative 180 degrees Celsius, but inside it's a warm, humid greenhouse powered by a small nuclear reactor. Farmers grow genetically modified potatoes under LED lights. Engineers drill deeper, searching for hydrothermal vents, anything suggesting a warm layer beneath the ice. And the scientists? They're the real lucky ones. They have direct access to a liquid ocean that might have existed for billions of years. Every sample they pull up is a potential history book of alien biology. But let's be honest, we're not there yet. Not even close. The technology to build a self-sustaining subsurface base on an icy moon is still a wish list for dreamers. The power requirements alone are staggering. But that's the point. Ganymede forces us to stop thinking like tourists and start thinking like settlers. We're not just visiting, we're building a home. And that requires a different kind of courage. The kind that says, yes, the ice will crack, the radiation will test us, and the distance will break our hearts. But we'll build anyway, because that's what we do. And that is the question. A question that grows heavier with every mile we travel outward from Earth. Because Ganymede, more than any other world in our solar system, seems to hold a terrible mirror up to our own assumptions about life. We have spent decades imagining the universe as a buzzing, crowded place. We look at the billions of stars and we feel a kind of cosmic loneliness, sure, but we also feel hope. The math of the Drake equation, that famous old party trick of astrophysics, always seems to suggest that the universe should be teeming with chatter. Radio signals flying between civilizations like cosmic carrier pigeons. But when we turn our ears to the sky, we get silence. A deafening, crushing silence. That is the Fermi Paradox in a nutshell. Where is everybody? Now, let's take a step back and look at Ganymede with that question burning in our minds. It's not just a moon, it's an archetype, a blueprint, a cosmic prison built on a scale we are only just beginning to understand. Because here is the terrifying implication of the icy prison hypothesis. It suggests that the universe is not barren at all. It suggests that it is full of life, teeming, swimming, evolving life. But that life is trapped forever. Ganymede's ocean, hidden under 100 miles of ice, is a perfect laboratory for this idea. You drill down, you break through the crust, you find a dark alien sea heated by tidal forces, rich in minerals, protected from the vacuum and radiation of space by that massive frozen shield. And inside that ocean, life thrives. Microbial life, complex life, maybe even something with a rudimentary form of intelligence. A creature that has never seen a star. A creature for whom the entire universe is a cold, dark ocean, bounded by ice above and a rocky core below. It has no concept of the surface, no concept of space, no concept of anything outside its own liquid world. And if that is the case for Ganymede, why would it be any different for the other ocean's moons? For Europa, for Enceladus, for the countless other icy bodies we suspect exist in the outer solar system and beyond? Suddenly, the Fermi Paradox doesn't look like a question of rarity. It looks like a question of geology. Life may be a chemical inevitability given the right conditions. Every warm, wet, rocky world may brew it up like a pot of coffee. But intelligence, technology, and the will to escape your planetary ocean might be the rarest miracle of all. Most life in the universe, perhaps the overwhelming majority of it, is born, lives and dies, without ever knowing that there is a sky. They are trapped in their own version of Ganymede, an ocean world, an icy prison. They never build radio telescopes. They never launch rockets. They never see the stars because they have no idea the stars exist. And that brings us to the most sobering thought of all. The implication that sends a chill down the spine of every astrobiologist. Ganymede might be the norm, Earth might be the freak, we are the anomaly. The one species in our own solar system that broke out of the ocean, that looked up, that built a civilization on the dry land of the surface. And if life is common, but cosmic ionization is the rule, then we are not just explorers. We are the first, the only ones in our local neighborhood who can see the stars. Think about that for a moment. Every whale in the ocean of Earth has a wider perspective on the universe than any creature in the ocean of Ganymede. And we are the ones who figured out how to leave the water. We are the ones who built the ships. The responsibility that comes with that is immense. It is not just a scientific curiosity. It is a moral imperative. If we are the only species in this solar system that can see the stars, then we are also the only species that can save them. We have to go to Ganymede, not just to drill through the ice, but to look back, to understand what it means to be the watcher. The one who sees the ocean from the outside, the one who knows that somewhere down there, in the dark and the cold, something else might be alive, waiting, unaware, and that awareness, our ability to see the stars, might be the most precious, fragile, and terrifying gift in the entire galaxy. And so, here we are, staring at an ocean that should not exist, kept warm by a cosmic engine that will not run forever. That is the thing about Ganymede. It is not a permanent paradise. It is a ticking clock. The Laplace resonance, that perfect orbital dance between Io, Europa, and Ganymede, is not eternal. Over time, the tidal forces that squeeze and heat Ganymede's interior will slowly decay. The moon will drift, the heat will fade, and that hidden ocean, warm enough to perhaps host life right now, will begin to freeze. We are talking about a geological timescale. Not tomorrow, not in 1,000 years. But in the grand, slow march of the solar system, that window of habitability is finite. It opens, it closes. And right now, we happen to be living in the brief, precious moment when it is open. So what does that mean for us? It means we have a now window. A narrow slice of cosmic history where the conditions are right, not just for life to exist on Ganymede, but for us to find it. Humanity has the technology, curiosity, and sheer audacity to send a probe down through that crust and into the water. But we have to move, because the longer we wait, the colder it gets. Every year we delay is a year closer to the moment when that ocean goes silent. And if there is something alive in there, something ancient and alien, we may never get another chance to meet it. That is what makes this terrifying. Not the landing itself, not the radiation, but the quiet, patient pressure of time. We are the ones who know. We are the ones who see the clock. And the question is simply this: will we act before it runs out? Here is a popular and persistent objection, and it sounds incredibly reasonable at first. Why should we risk everything now? Why send humans, or even fragile robots, into that crushing radioactive hellscape when the technology will be better in 50 or 100 years? Leave it for the next generation, right? Wrong. Dead wrong. That tidy little escape hatch, that comfortable deferral, is a lie dressed up in the cloak of prudence. The people who will design the first probe to slip beneath those icy crustal plates are alive today. They are sitting in university labs right now, tinkering with pressure seals and radiation-hardened circuits. The scientists who will decode the first genetic samples of an alien ecosystem are currently in middle school learning the periodic table. This is not a problem for the unborn. It is a challenge for the living. If we wait, we do not just delay a mission. We lose institutional knowledge, momentum, and the funding cycles and political will that flicker and die across a single generation. We are the first generation with the tools and the terrifying clarity to see what is down there. To kick this can down the road is not wisdom. It is cowardice dressed up in a lab coat, and cowards do not discover new worlds. We stand at the edge of the greatest frontier we have ever known, not with a telescope or a rover, but with a question that cuts straight to the bone. The true limit here is not our technology. It is our maturity. Think about that for a second. We have the blueprints. We have nuclear batteries and radiation-hardened computers. We could land something on Ganymede within a decade if we threw enough money and stubbornness at the problem. But the real question, the one that keeps planetary protection officers awake at night, is whether we have the humility to be careful. Because here is the thing we rarely talk about. Ganymede is not just a rock. It is a pristine alien ocean world sealed under 100 miles of ice. If we land there, we might bring Earth. Bacteria, spores, microscopic hitchhikers that survived the journey. And if we contaminate that ocean, we will never know for sure whether the life we find is real or just our own dirty fingerprints. It would be the greatest scientific failure in human history. So the true limit is this. Can we wait? Can we build a probe so sterile it hurts? Can we accept that the first humans to touch Ganymede might not be us, but something evolved in a completely different chemical soup? The question is not if we will reach it. It is whether we will be wise enough to do so carefully. That wisdom takes time. It takes sacrifice. It takes the kind of patience our hyperactive culture does not excel at. But this is not a race. This is a first contact. And first contact demands that we come not with a flag and a drill, but with quiet reverence and a whole lot of restraint. And that restraint, that patience, it brings us, finally, to this moment, to the edge of everything we know and the beginning of everything we might become. Because this journey, this long, painstaking, decades-long crawl through the solar system, it was never really about ice, or radiation, or even an ocean. It was about a question. One single, overwhelming question that has quietly haunted the quietest moments of our species for generations. Are we alone? For the first half of this series, we talked about the hidden ocean of Ganymede as a scientific marvel, a geological curiosity. But as we stand here, looking back over the arc of this story, from the first grainy images of a strange grooved world, to the terrifying realization of Jupiter's lethal radiation belts, to the delicate, almost heartbreaking hope of a biosphere swimming in eternal darkness, we have to ask ourselves something far more uncomfortable. What if we find something there? Think about it. We spent centuries staring up at a silent universe, a cold, empty blackness that seemed to mock our every question, and then slowly, piece by piece, we started to realize that the universe might not be empty at all. It might just be quiet, incredibly, impossibly quiet. And here, on a moon we once dismissed as a frozen rock, we might be standing on the doorstep of the loudest answer humanity has ever heard. The discovery of a second genesis, a separate origin of life, right here in our own backyard, would change everything. It would shatter the old paradigm. It would tell us that life is not a freak accident, but a cosmic imperative. That biology, not physics, might be the universe's default state. But that same discovery carries a weight we are not prepared for. The weight of responsibility, because if we find life on Ganymede, we have to ask the really hard questions. Do we have the right to drill into that ocean? To send probes swimming through a world that has never known the touch of a sunbeam? Or do we have a duty to do nothing? To stand back, watch, and listen? To let that alien biosphere evolve in its own time, without our clumsy, well-meaning interference? That is the defining scientific question of the 22nd century. Not how to get there, but what to do when we arrive. Because this isn't just a story about a moon, it's a story about us. About who we are as a species. Are we explorers, driven by an insatiable need to know? Or are we caretakers, humble enough to leave a miracle alone? The tension between those two impulses is the very engine of our future, and it is a tension we have not yet resolved. We have the technology. These instruments are being built as we speak. The JUICE spacecraft is already out there, threading its way through the solar system, on a course that will bring it to Ganymede's doorstep in just a few years. The clock is ticking. The window is open, but the choice is still ours. Do we have the curiosity to go, the courage to face whatever answer we find, and most importantly, the wisdom to handle it? These are not rhetorical questions. They are the most practical, urgent, and terrifying questions we have ever faced, and they demand an answer. If you want to follow the journey of JUICE and the next generation of explorers, subscribe to This Is Space. The next chapter of this story is being written right now, and we'll be here to tell it, because out there, in the cold, silent shadow of Jupiter, beneath miles of ancient ice, Ganymede is waiting. It has been waiting for billions of years. Through the rise and fall of dinosaurs, through the birth of civilization, through every war, every discovery, every quiet moment of wonder, it has waited, and for the first time in history, so are we wait. But waiting is not a passive state. It is a charged, electric, expectant silence. The kind that fills a room before a diagnosis is read, the kind that hangs in the air before a verdict is delivered. For our entire history as a thinking species, the silence from the stars has been the most profound fact of our existence. The Great Silence, they called it. Enrico Fermi looked up at the night sky in 1950 and asked, "Where is everybody?" It was a question that has haunted every subsequent generation, and the answers were never comfortable. Maybe intelligent life destroys itself before it can reach the stars. Maybe the universe is filled with life, but we are beneath notice. Maybe the silence is a warning. Do not broadcast your location. Do not attract attention. But Ganymede offers a third possibility, a quieter possibility. Perhaps the silence isn't a warning at all. Perhaps it is merely patience. Perhaps life takes time. Not just 10,000 years, or 1,000,000, but billions. Perhaps the universe is not empty, it is simply young. And we are standing at the dawn of a biological epoch, watching the first tentative steps of a new kind of life. Not on a distant planet orbiting a distant sun, but right here, in our own solar system under miles of ice, in a saltwater sea that has never known a shore. History teaches us that every great discovery comes with a shadow. When Copernicus moved the Earth from the centre of the universe, it was not a simple scientific correction. It was an existential wound. We were no longer special. We were no longer the focus of creation. We were a pale blue dot, adrift in an indifferent void. That wound has never fully healed. It is the driving force behind our obsession with Mars, with Europa, with Enceladus, with every hint of water and warmth. We are looking for company, not just to satisfy curiosity, but to heal a loneliness we have felt for 400 years. And yet, if we find life on Ganymede, the wound will change. It will not be healed. It will be transformed. We will learn that we are not alone in our solitude, but part of a vast, slow, patient tapestry of biology that has been weaving itself quietly in the dark for eons. The microbial life of Ganymede. If it exists, is not our cousin, it is our contemporary. It began its journey at the same time we began ours, in the same stellar nursery, under the same sun. It just took a different path, a stranger path, a path that led into the abyss rather than toward the light. Think of the biochemistry. On Earth, life is built around the sun. Photosynthesis is the engine. Energy flows from above, down through the food chain, warming the surface, lighting the day. But on Ganymede, life would be built around chemistry, around hydrothermal vents, around the slow, energetic dance of hydrogen and sulfur, of methane and carbon dioxide in the total absence of a single photon. It would not be green. It would not follow a day-night cycle. It would not know the seasons. It would exist in a state of eternal, unchanging midnight, driven only by the slow heat of a planetary core and the tidal flexing of a gas giant's gravity. It would be the most alien thing we have ever encountered, and yet it would be our neighbour. The waters of Ganymede are deep, estimated to be over 100 kilometres deep in places. That is 10 times the depth of the Mariana Trench. Imagine the pressure, imagine the darkness. Imagine a world where the only light comes from the faint ghostly glow of bioluminescence, if any life has evolved that ability at all. We have no idea what form that life might take. It could be simple. A microbial slime clinging to rocks, breathing sulfur. It could be complex. Swarms of creatures, slow and ancient, drifting through a sea that has no surface and no bottom. It could be intelligent. A civilization of creatures that has never seen a star, that has no concept of up or down, that has built its entire understanding of the universe based on sound, pressure, and chemistry. And we are about to knock on their door. That is the weight of this moment. That is the burden of the 22nd century. We are not just scientists, we are ambassadors. We are the first contact team for the entire human species, and we have no training, no protocol, no idea what to say. The SETI community has spent decades debating how to respond to a signal from the stars. But what do you do when the signal is not a radio wave, but the faint trace of organic molecules in a water sample? What do you do when the first hello is not a prime number sequence, but a cell, a single, fragile, alien cell, floating in a drop of water, billions of kilometers from home? The answer is not simple. It is not found in any textbook. It is found only in the question itself. And Ganymede is asking that question right now in this very moment, as the ice shifts and the currents flow and the darkness remains unbroken. We have a choice to make, and we do not have forever to make it. The clock is ticking. The probes are being built. The doors are opening. And on the other side of that door, in the silent, frozen ocean of a forgotten world, something is waiting to be found, or left alone. The question is not whether we can go. The question is whether we should. And the answer to that question will define not just our future, but the future of every species that shares this solar system with us. Ganymede is waiting, and for the first time in 4 billion years, the waiting might be over.